We're continuing to bring you live imagery of the lunar surface from the Orion spacecraft as it continues to close in. Orion is currently 3,091 miles away from the moon, traveling at a velocity of 4,238 miles per hour. If you're just joining us this morning, we are 1 hour and 18 minutes away from today's outbound powered flyby burn. This burn will be 3 minutes and 27 seconds long and will propel Orion around the moon in anticipation of a splashdown off the coast of California on December 11th. Leading the team here in Mission Control Houston during today's burn is NASA Flight Director Judd Freeling. But Judd is not the only flight director here at the Johnson Space Center in Houston, Texas, that is working the Artemis mission. So let's take a look at a few of the other flight directors.
Flight CTO on the flight loop.
Buddy comfort cooling status.
Conoco AOS, good for copy.
Flight controllers generally focus on systems, subsystems of the vehicle, and they're more in tune with the detailed workings of their particular system that they're responsible for. Flight directors, on the other hand, are more in tune with what is the integration between all of the subsystems. What are we all marching towards? What's our mission objective?
Prop flight has the RCS holding together with the regs.
Really, your training starts when you become a flight controller. You know, you learn a lot by osmosis, and you kind of get a sense of a little bit of the job, but once you become a flight director, the amount of learning you do is exponential.
You don't become an expert, but you have to understand at a depth where you could have the good conversation, ask the right questions to the experts who are the flight controllers. You spend a lot of time studying and then training, getting in simulations and running through all the motions and practicing the real-time situation scenarios in the training environment.
I am the ascent and entry flight director for Artemis 1. I will take responsibility of the vehicle after it launches. I'll also be the entry flight director, so once we come back to Earth, I'll have a team that will monitor and control the vehicle once it splashes down, and we hand that over to Melissa Jones, who is the NASA recovery director.
Splashdown. Touchdown verified. Copy.
I'm the lead flight director for the mission, really responsible for the overall development of the mission. We work directly with the programs. They provide us the mission priorities, and we build a timeline that's going to accomplish those mission objectives. We're responsible for building our team, getting our team trained and certified. And we have a training team that helps us, but we have the overall responsibility for putting together the team that's going to execute the mission.
Confirmation of translunar injection burn cutoff.
When you go to a place like the moon or Mars, you really have to be explorers. It pushes the boundaries of civilization.
We are having to develop new technology that's going to have to sustain the astronauts for these very, very long trips. And it just makes sense to test that and going to the moon where you're in a similar environment, but you're much closer, and in the event of an emergency type scenario, we can bring them safely back home.
Station, this is Houston.
We've had a lot of experience now in low Earth orbit, over 50, 60 years of experience, and we've learned how to do that pretty well. We've learned what the effects of the body are in low Earth orbit, but there's still things that we need to practice, and we need to be able to understand how you sustain life further and further and further away from our planet.
It's just so different from everything you learn when you do low Earth orbit. And that's what's making it so much fun. I'm every bit as excited about this mission as I was the first day I walked in the doors of Mission Control.
Orion continuing to close in on the moon, now 2,774 miles away, traveling at a velocity of 4,300 miles per hour. And you are looking at a view of the bottom of the European space You are looking at a view of the European Service Module, the very bottom of it there. And you are seeing the large engine there in the center of the European Service Module. That's the Orbital Maneuvering System engine, or OMS engine. That's the engine that will be utilized during today's return power flyby burn. This is the main engine on the European Service Module and is a repurposed Space Shuttle Orbital Maneuvering System engine that has flown in space 19 times before, all on Space Shuttle flights, beginning with STS-41G in October 1984 and ending with STS-112 in October 2002. We are now 1 hour and 13 minutes away from today's return-powered flyby burn. That burn will last 3 minutes and 27 seconds, and will change the velocity of the Orion spacecraft by 960 feet per second. You're also getting a great view of the 8 auxiliary engines on Orion. And again, Orion continues to close in on the moon, now only 2,680 miles away from the lunar surface. Following today's closest approach to the moon, Orion will be only 79.2 miles above the lunar surface. We're now 1 hour and 8 minutes away from today's return-powered flyby burn. Everything continuing to move smoothly here in Mission Control, Houston. As a reminder, we will lose signal when Orion crosses behind the moon. That's because the moon will be blocking the signal to the Deep Space Network. We are anticipating that loss of signal 1 hour and 5 minutes from now. That will be a 30-minute loss of signal. During this loss of signal period is when Orion will complete the return-powered flyby burn, that 3-minute and 27-second burn that will send Orion on a trajectory to head back home ahead of a splashdown in the Pacific Ocean on December 11th. And if you are just joining us this morning, we are bringing you live coverage of today's return-powered flyby burn here in Mission Control, Houston. That burn is 1 hour and 6 minutes away from now and will be a 3-minute, 27-second burn that will slingshot Orion around the moon in a trajectory to head back to Earth and a splashdown on December 11th. But we have been getting some beautiful views of the moon, and I have a very special guest with me this morning. This is Juliana Gross. She's the Deputy Apollo Curator, and she's going to point out some of these amazing features that we have been seeing on the lunar surface in some of the shots that we have been getting. So thank you so much for joining. I really appreciate you taking the time.
You're very welcome. I'm very excited to be here.
Yes, absolutely. So can you talk a little bit about some of the features that we are seeing on the lunar surface here?
Yeah, absolutely. So if you look on the moon right now to the left middle area of the moon there, the bright spot that you see there, that's Copernicus crater. The dark region that is sort of like right in front in the middle center of the moon right now, that's the Imbrium basin. And so these are impact features that we have on the moon. So when the moon formed throughout its history, over its 4.5 billion years, has been bombarded by meteorites and asteroids. And for the Imbrium, that's the darker round area that you can see there, what happened is it's a massive crater, and so we call these a basin, and melt from the interior of the moon came up through cracks and then filled that basin crater. And you can imagine that as a big lava lake, and then it cooled to form basalt. The same thing happens at the moment on Earth. Hawaii is erupting, and that brings up basalt from the interior of Earth. So these basalt samples, when we analyze them and we look at these, we can learn something about the interior of the moon. I see that we lost our actual live view, but in this beautiful view that we can see here, you can really nicely see Copernicus right in the center, and that's brighter because it excavates crustal material, which is white or bright, compared to the mare, which are basalt, which is dark. Oh, there we are back. So Copernicus is now in the lower right corner of that image. That's a fairly young crater, and that's why it still appears fairly bright, because over time, when the sun interacts with lunar rocks, it darkens over time, so we call that space weathering. Yeah.
And so we are flying fairly close to some of the Apollo landing sites now. We're a little too high above. We're about 2,000 miles away from the moon still to make out any features. But can you talk about a little bit about what the Apollo program studied in those landing zones, and maybe touch on how Artemis is going to be different, because we're going to be landing in an entirely different spot, right?
Yeah, absolutely. Apollo wasn't so much about science. It was more about like, hey, we're actually going to the moon and we can do it, and like the technology to show that we can do it. Apollo 14 and 12 sort of landed near Copernicus, like south of where Copernicus crater is right now that I pointed out in that region. And so Apollo 14 landed there in 1971, right above the Framora region, which is kind of like south of Copernicus, and it's right at the edge of that big Imbrium basin that I talked about. They brought back a lot of rocks. They were interested in the rocks that were excavated from Imbrium. So there's a lot of impact melt, as we call them, or breccias. And every time a rock gets exposed to like heat and pressure and started to remelt in like an impact event like that, it resets the internal clock. So when rocks form, they record the condition from which they formed, including the age, like the time when they formed. But every time there's an impact event and it gets remelted, that internal clock resets. Now we can take these rocks and then measure the ages of them. And so every time the clock got reset, we now have the age of that impact event. And so we want to know when Imbrium formed, because it's such a big event that happened on the moon, that we can put everything else in relative age to each other. So that why that mission was important. Apollo 12 landed in the Oceanus Procellarum region, which is sort of to the lower left and then going up. It's kind of like where that shaded, like where you kind of stop seeing the moon, you know, the boundary of the shade and the sunlight lit area. The little bright spot that comes up on the, what is that, lower left third of the moon, that is Aristarchus crater. So that's a super bright crater in that Procellarum region, which we're now seeing more and more of. So that's sort of the area where Apollo 12 landed. That landing was to sort of show that we can do a pinpoint landing. So they landed 200 meters away from the Surveyor 3 lander, and they actually brought a piece from Surveyor 3 back to Earth to like really show. And that then paved the way for future missions to like really like, hey, we can do a pinpoint landing. So we can go to like a more difficult terrain where we can land, where it's more ruggedy. And so that's where we went there. And so now you can see even more of the Procellarum region. Most of that is dark gray, as you can see, and so these are the basalts, and that mission brought back a lot of these basaltic materials. And then we can look at the ages, and it turns out that those basalts were very different, and they were younger than the Apollo 11 mission, than the rocks that they brought back, the basalts that they brought back. Now, Artemis is going to be super exciting because we're going to a very different region. So if you look at the surface here, and you can see that's mostly dark gray, so it's mostly basalts. You can see in the upper part of the moon that's still bright. That's what we call the highland crust. So that's the very old crust. So when the moon formed, there was a giant impact between two protoplanets. It collided, created a lot of heat, everything melted. The center part formed and became Earth. And then the debris cloud that surrounded it coalesced and then became the moon. So once upon a time, the moon was covered in a global magma ocean. So it was fully molten, right? And if you have a global magma ocean, you start crystallizing things. So now when you crystallize stuff that is denser than the melt, that sinks, right? And if you crystallize things that are less dense than the melt, that starts to float, like ice is floating on water, right? And so now we have these crystals crystallizing these minerals, and they are less dense, so they float to the surface and they build the crust. These crystals are called plagioclase. They're white. And so your crust that then forms on the moon is white. And that's why the moon looks so bright when you look at this image or in the night sky, because that's the old crust of, you know, the oldest rocks we have, and they're white in color. And so that's why this is so bright. Now the near side, so the side that we see right now, we see these dark patches, which then are the younger basalts that came to the surface once you start impacting it, and you take stuff away, you make these big basins, and then the interior remelts, and that melt comes up to form to fill these craters. That's very special. So it turns out that this Procalarium region where Imbrium sits in, where Apollo 12 landed, where Apollo 14 landed, all these rocks that were brought back, they rocks, right? You get, geologically speaking, really interesting rocks, but they're not representative for the United States or the rest of the world, right? So same happens with Apollo. Really cool rocks, geologically speaking, very interesting, lots of basalts, right? They all have this weird creep component, so they're all creepy. But the rest of the moon is very different, so they're not representative. Now with Artemis, we're going to go to the South Polar region. So that region is more representative compared to Apollo. We don't really expect a lot of basalts there, so that's more like highland region. The South Polar region also has the largest impact basin that we have on the moon, and also the oldest. So if we can bring back rocks from there, we can hopefully date that really, really old impact region, and then get a better idea of when things happened on the moon and establish a timeline. Now we also know that the polar regions are really, really cold. And so ices or volatiles and gases on the moon, they freeze out in the polar region. So when we go there and collect rocks, we can also bring back these frozen samples and then learn something about where the water is coming from, whether it's moon or, there was lots of asteroids and comets that impacted the moon, and then so we can also learn about something about the water that was delivered to the Earth-Moon system, which most likely also ended up on Earth. And so we can learn something about our own history and how the moon formed and evolved over time better than we can with Apollo. We're missing a lot of rocks and processes with Apollo, and hopefully we can fill these gaps with Artemis.
You are a wealth of knowledge. Thank you so much for sharing all of that information. Now, as we continue to get closer and closer to the lunar surface, of course, these features are going to become more and more clear. Orion is now 2,000 miles away from the moon, but at closest approach today, it will be just about 80 miles above the lunar surface. So before you go for the day, it looks like we are starting to get some better views of that area that you were discussing before. Is there any other items or areas that have come into view since we've been chit-chatting that you think would be helpful to point out?
Yeah, so we see Kepler crater, which is sort of to the left and lower left of Copernicus, what I just pointed out. So it's this like grayish area with a little dot in the center. And then if you go from there further to the right at where the moon's shades are, so that's still the lower left, that really bright area, that's Aristarchus crater, and that's a really young crater, and it's really bright because it brought up material from that crust that I said, and that's this white rock. It turns out we have orbital reflectance data. So when we look at the light, the sunlight that gets reflected off the surface, we can make assumptions about the chemistry in that region. And it turns out that that region is, geologically speaking, really, really complicated. So it brought back up old crustal material, but we also see some basaltic material. And in the central peak, we see material that is silicic, so it's really, really high in silica, and that usually means there's some kind of evolved rock. And when we say evolved, on Earth, that usually means like granites and stuff like that. We don't really mean it that way here, but it has more silica content in it. When I say central peak, so what happens when you have a big impact into the crust rebounds and brings a central part comes up. If you think about it, throwing a rock into water, right, it makes a splash, and then the water rebounds and brings a kind of like a central thing up and then plops back down. So if you would freeze that water, it would stand up in the center. So that happens on the moon or on Earth as well, where like the crust rebounds. And so the central peak is the area that is the deepest material that got brought back to the surface. So that is of importance and special interest to scientists, because now we have another window into the interior of the moon to study these things. And it turns out, specifically for that little bright crater there, it's super complicated, and then we're still trying to figure out what we're seeing.
So it sounds like there's definitely much to be learned from the moon, especially through the Artemis program, and I'm sure you're looking forward to getting some of those samples back to be able to study in depth.
Oh, absolutely.
Well, thank you so much, Juliana, for taking time out of your day to chat with us. I really appreciate it. I hope you have a good rest of your day.
Thank you so much, and thank you for having me. This is fantastic.
We're now 50 minutes away from today's return-powered flyby burn. This burn will slingshot Orion around the lunar surface and put it in a trajectory ahead of a splashdown on December 11th back on Earth. This burn will be a 3-minute and 27-second long burn and will be the longest burn of the mission utilizing the Orbital Maneuvering System, or OMS engine. You are getting a view of the OMS engine on your screen. It's in the very top left, the largest engine on your screen. The next major milestone that we're tracking here in Mission Control Houston is the Go, No-Go poll. During this poll, NASA Flight Director Judd Freeling will go around the room and poll each of the flight console positions to ensure that all is looking good ahead of today's burn. Orion is now less than 2,000 miles away from the moon, 1,756 miles, moving at a velocity of 4,563 miles per hour. At this time, Orion is over 237,000 miles away from Earth. And if you're just joining us, Orion is now 1,550 miles away from the moon. We are anticipating today's return powered flyby burn to begin 43 minutes from now. This burn will last 3 minutes and 27 seconds. During the time period that the burn takes place, Orion will be in a loss of signal period because it will be directly behind the moon, and the moon will be blocking the signal with the deep space network. Today's loss of signal will last for 30 minutes. After we come back around to the other side of the moon, we anticipate regaining communications with the Orion spacecraft, and that's when the team here in Mission Control will be able to analyze the return-powered flyby burn and make sure everything went as expected. This burn is critical as we look ahead to a return and splashdown of the Orion spacecraft on December 11th. Today's burn will put us in a trajectory to enable that splashdown. And on your screen right now, you are seeing some movement here. This is taking place as the solar array wings get into the right configuration ahead of today's burn. A great view of the Orbital Maneuvering System engine, or OMS engine, coming into view on the European Service Module. That's that large engine on the very bottom of the European Service Module, and is the engine that will be used during today's 3 minute and 27 second burn. Again, this will be the longest burn done by the OMS engine so far, but the OMS engine can actually fire for up to 16 minutes if necessary. You're also getting a view of the 8 auxiliary engines on Orion. These engines can fire for less than 1 minute, up to 45 minutes in length. And these engines are used more for trajectory corrections. Each engine provides about 100 pounds of thrust and can provide steering during burns by pulsing on and off. Orion continuing to get in the proper orientation ahead of today's burn. We are tracking that burn 38 minutes from now. And again, during that burn, we will lose signal with the Orion spacecraft. The loss of signal will be 36 minutes from now. You're looking at a view from our data-driven animation of the Orion spacecraft. As you can see, we're now 1,317 miles away from the moon. Orion moving at over 4,700 miles per hour. At this time, Orion is over 238,000 miles away from Earth. Everything continuing to move smoothly this morning as we anticipate the return powered flyby burn 36 minutes from now. We are hearing that the Orion spacecraft is now in the proper attitude ahead of today's burn. From this view, you can see that orbital maneuvering system engine on the left of your screen, that large engine on the European service module. That's the engine that will be utilized during today's burn. You also see two of the auxiliary engines, as well as two of the solar arrays. On the tip of the solar arrays, on the wings of the solar arrays, are the SAW, or solar array wing cameras. Those are the cameras which are capturing the imagery that you see right now on your screen. Orion continuing to close in on the moon, now 1,100 miles above the surface of the moon. During today's closest approach, Orion will be just 80 miles above the surface of the moon. Here in just a couple of minutes, we do expect NASA Flight Director Judd Freeling to give a go, no-go poll for today's return-powered flyby burn. If the team polls go, then we are anticipating the burn to begin at 10:43 a.m. Central and last 3 minutes and 27 seconds. While Orion is behind the moon today, we will not have communication with the vehicle because the moon will be blocking the connection to the Deep Space Network. However, once Orion swings back around on the other side of the moon and regains communications with the Deep Space Network, we do anticipate to be able to communicate with the vehicle. Today's loss of signal is slated to last 30 minutes. And at this time period, we are now 1 hour away from, we are now 29 minutes away from the loss of signal and about an hour away from the acquisition of signal. If you're just joining us this morning, we are bringing you live coverage of today's return-powered flyby of the Orion spacecraft, which is now 20 days into its 25-and-a-half-day test flight. While this Orion spacecraft is uncrewed as part of Artemis 2, we will have crew on board Artemis 2. Today's return-powered flyby will begin at 10:43 a.m. Central and will last 3 minutes and 27 seconds. This burn will slingshot Orion around the backside of the moon and put it in a trajectory ahead of a splashdown off the coast of California just a few days from now on December 11th. During Orion's mission, it broke the record for longest distance traveled away from Earth for a human-rated spacecraft meant to return back to Earth. On November 28th, Orion broke that record, having traveled 268,563 miles away from our home planet. During this time period, Orion was in the distant retrograde orbit. Orion remained in this distant retrograde orbit for about 6 days, in which we tested out the systems of the spacecraft in the deep space environment. Last week, the distant retrograde departure burn took place, which brought Orion back towards the moon, which we are now less than 1,000 miles away from. The DRD burn set us up for today's return-powered flyby burn. And this burn again sets us up for splashdown just a few days from now. And here is the view of the moon, as mentioned, less than 1,000 miles away. Still a little ways to go to get to our closest approach of the day, at which point Orion will be just 80 miles above the lunar surface. But we are getting closer to today's anticipated burn, now 27 minutes away from that burn, and just 24 minutes away from the anticipated loss of signal. Orion continuing to pick up speed as it closes in on the lunar surface, now traveling at 4,852 miles per hour, and now just 846 miles away from the moon. We're continuing to get a shot of the Orion spacecraft, namely the European Service Module and the Orbital Maneuvering System, or OMS engine, on the left hand of your screen there, the largest engine shown. That's actually the largest engine on the Orion spacecraft. The OMS engine is a repurposed Space Shuttle Orbital Maneuvering System engine that has flown on 19 Space Shuttle flights. The first flight was STS-41G in October 1984, and the last was STS-112 in October 2002. And the go, no-go poll for the return-powered flyby is now underway. And the team here in Mission Control Houston did poll go for today's return-powered flyby burn. That burn will take place 23 minutes from now. And with the go from the team here in Mission Control Houston for the return powered flyby burn, we're now just counting down the minutes until the start of that burn. Again, 22 minutes away from today's burn. This burn will last 3 minutes and 27 seconds. But just prior to the burn, we will lose signal with the Orion spacecraft. That loss of signal is anticipated in 19 minutes from now. The reason we do lose communication with the spacecraft is because it will be flying directly behind the moon, and the moon is blocking the signal to the Deep Space Network. However, once the spacecraft travels back to the other side of the moon, we do expect to regain communications with the vehicle at that time. Orion is now only 687 miles away from the moon. At closest approach today, Orion will be just 80 miles above the lunar surface. Now just 20 minutes away from today's return-powered flyby. This burn will commit Orion to a trajectory to head back to planet Earth after its 20-day mission so far. By the time Orion splashes down in the Pacific Ocean, it will have been in space for 25.5 days. During its journey, Orion has broken the record for longest distance traveled by a human-rated spacecraft meant to return back to Earth. On November 28th, Orion was 268,563 miles away from planet Earth. Right now, Orion is 239,364 miles away from Earth, but only 570 miles away from the Moon. At our closest approach today, Orion will be just 80 miles above the surface. Our next set of events will take place in rapid succession. First, we will lose signal with the Orion spacecraft as it travels behind the moon. That loss of signal will be just 15 minutes from now. Then 3 minutes after we lose signal with Orion, the return-powered flyby burn, or RPF, will take place. This burn will last 3 minutes and 27 seconds and will be completed with the Orbital Maneuvering System, or OMS engine, which you see there on your screen to the left on the European Service Module. It's the largest engine on Orion. And today's 3 minute and 27 second burn will be the longest burn that the OMS engine will have completed on the mission so far. And we're continuing to get some great views of the lunar surface as we fly just 500 miles overhead. This view coming from one of the solar array wings or SAW cameras as it gets into the proper position for today's burn. Coincidentally, 8 years ago to the day was the launch of the Exploration Flight Test 1, or EFT-1. This was the first test flight of the crew module portion of the Orion multi-purpose crew vehicle. This was an uncrewed test flight that orbited the Earth 2 times before splashing down. Now, 8 years later, Orion is about to fly behind the moon. We're 15 minutes away from today's burn. We're now 13 minutes away from today's return-powered flyby burn. Orion is 365 miles above the lunar surface, traveling at a speed of 4,963 miles per hour. Just 10 minutes from now, we do anticipate losing signal with Orion as it begins its trip around the backside of the moon. On the bottom of your screen in the left there, you can see the solar array as it begins to move into place. You're also looking at the Orion capsule itself there, taking up the majority of your screen. You can see the kind of silver coloring of the capsule. This is the portion that when we have a crew on board as part of Artemis 2 that they will be living and working in during their trip to the moon and beyond. And in the top left of your screen there, you can see the moon as Orion glides over it, again 335 miles above the surface. But at the closest approach during today's return-powered flyby burn, Orion will be just 80 miles above the lunar surface. We are hearing that the solar arrays are configured for today's burn. Orion is now moving to the proper burn attitude. We're now 10 minutes and 30 seconds away from the start of today's 3-minute and 27-second burn. And we expect to lose signal with Orion in 8 minutes. Today's return-powered flyby burn sets us up on a trajectory to splash down off the coast of California just a few days from now on December 11th. And you were seeing some thruster firings there as Orion maneuvers to the proper attitude for today's burn. Now less than 6 minutes, 30 seconds until we lose signal with Orion. The burn will start in 8 minutes and 40 seconds. Orion is currently 253 miles above the lunar surface. Today's 3-minute and 27-second burn will take place with the Orbital Maneuvering System, or OMS engine. That's the largest engine on the European Service Module. Today's burn will change the velocity of the spacecraft by 960 feet per second during its 3-minute, 27-second burn. Closing in on 5 minutes away from our anticipated loss of signal with Orion. We will not have signal with Orion because the moon will be blocking out the signal to the Deep Space Network. However, when we swing back around on the other side of the moon, we do anticipate to regain those communications. And we are hearing that Orion is in the proper burn attitude. 6 minutes and 40 seconds away from the start of today's 3-minute, 27-second burn. Just 4 minutes until today's loss of signal. As you can see from this telemetry-driven animation, Orion is now 202 miles away from the lunar surface. And you're looking at a live view inside the White Flight Control Room here at the Johnson Space Center in Houston, Texas. NASA Flight Director Judd Freeling is leading the team on console at this hour. We were tracking a loss of signal about 2 minutes and 40 seconds from now, but we are hearing that we did get that loss of signal a little earlier than expected, but that is to be anticipated from time to time. So now the next major milestone that we'll look ahead towards is the return-powered flyby burn less than 5 minutes from now. While we are traveling behind the moon, we do not have signal with the spacecraft because the moon is blocking the connection to the deep space network. We anticipate that loss of signal to last about 30 minutes. And our counterparts here in this shot here in the European Space Agency Control Center in Noordwijk in the Netherlands. The European Space Agency's contribution to Artemis is, of course, the European Service Module, where the Orbital Maneuvering System, or OMS, engine is located. That's the engine that will be used for today's 3-minute and 27-second burn to propel us around the backside of the moon and commit us to a trajectory back to Earth ahead of a splashdown on December 11th. We're now less than 3 minutes away from the start of that 3-minute, 27-second burn. Right now, we do not have signal with the Orion spacecraft. That is expected as the vehicle is traveling behind the moon. This loss of signal will last about 30 minutes. And as Orion comes back around the other side of the moon, we will be able to regain communications with the vehicle. Now less than 2 minutes from today's return-powered flyby burn. And you do see the team here in Mission Control stand up and stretch their legs right now. Oftentimes they'll use this time to catch a quick break while the vehicle is in the loss of signal period. Again, today's loss of signal is expected to be about 30 minutes in length. One minute until the start of today's return-powered flyby burn. "30 seconds until the start of today's 3-minute, 27-second long burn, committing Orion to a return home." "15 seconds until burn start." And we do expect the burn to be underway. Again, this is a 3-minute, 27-second long burn. Because Orion is behind the moon and we do not have signal with the vehicle, we will not be able to confirm that the burn has began or the results of that burn until we come back around to the other side and regain communications on the Deep Space Network. Today's burn is being completed with the Orbital Maneuvering System, or OMS engine. That's the largest engine on the bottom of the European Service Module. Today's 3-minute and 27-second long burn will be the longest during the Artemis 1 mission used by the OMS engine, but the OMS engine can fire for up to 16 minutes in length. Now approaching the 2-minute mark into today's return-powered flyby burn, 1 minute and 27 seconds remaining. We're approaching the 3-minute mark into today's burn. Again, this burn is critical as it will slingshot us around the backside of the moon and place us on a trajectory ahead of a splashdown off the coast of California. 3 minutes into the burn, 27 seconds remaining. And we do expect the burn to be complete at this time. Again, because we are behind the moon and do not have signal with the spacecraft, we will not be able to confirm until Orion comes back around the other side of the moon. We are anticipating that acquisition of signal about 24 minutes and 45 seconds from now. And if you're just joining us, the return-powered flyby burn, the burn that is going to send Orion back around the other side of the moon in anticipation of a splashdown next week off the coast of California, has completed. Orion is still behind the moon at this hour, and we are in a period of a loss of signal with the vehicle. We're anticipating to get that acquisition of signal back less than 24 minutes from now. But while Orion continues its journey around the moon, I do have a very special guest joining me today. This is Najud Moranci. She is the chief of the Exploration Mission Planning Office here at the Johnson Space Center in Houston, Texas. So thank you so much for joining us today, Najud.
Thank you. Glad to be here. Super special to be here for RPF.
Yeah, absolutely. It's an exciting moment indeed. This burn really commits Orion to a return journey home. But before we talk about that, I do want to talk a little bit about some of the work that your group is doing as part of the Artemis program. Now, this is an uncrewed test flight of the Orion spacecraft, but there's other components of Orion, including some robotics work that your group is working on. Can you talk a little bit about that and how it helps contribute to Artemis?
Yeah, there's a lot of different components to the Artemis as an enterprise, right? You know, Orion SLS, this is our crewed vehicle to the moon, but we're also working on systems like Commercial Lunar Payload Service, which is delivering science payloads to the moon very soon, in the next year or so, hopefully starting those launches. And that's really the precursor for all of the logistics and the elements we're going to need as we build out a whole exploration enterprise on the surface of the moon.
That's great. I'm looking forward to seeing those land soon. And another aspect of your group is astromaterials. So during Apollo, many lunar samples were brought back to study, but during Artemis, we're going to be landing in a different location on the lunar South Pole. So how will our studies be different, and what will we be looking for this time around?
Yeah, part of our directorate includes the astromaterials and the curation of those materials. So all of the Apollo samples that came home came here to Johnson Space Center, and we have a dedicated facility that maintains them, manages the samples to send out to the science community for investigations. And that will also happen, they already do that for other samples, like the comet samples that come back from Hayabusa and Genesis. And as we bring Artemis samples home, they'll also be managing those and curating them. And really some of the advances in the science and measurements that we can make today that we did not have in Apollo are already getting prepared.
Great. And the very last thing I wanted to chat with you about today was the moment we've all been waiting for today, the return-powered flyby burn that occurred just 7 minutes and 9 seconds ago. So you had talked a little bit about this burn and why the timing of it was important on a Twitter post that you had shared. So can you talk a little bit more about that for the folks who maybe didn't see that?
Yeah, so all of the burns are very well calculated for specific reasons. So these burns have to be executed within moments of the timing. But really what it's doing is it's timing the return trip to Earth and then targeting so that when Orion travels behind the Earth, that's when the Pacific Ocean will be underneath the entry corridor. So we're targeting for a very thin slice of atmosphere, and that's where we do our aero capture. So the atmosphere actually slows Orion down, and we need to make sure all of that is set up precisely so that we can enter the atmosphere while the Pacific is where the entry targeting is, so that we can be landing right where the recovery forces are. So there's a lot of calculations that go into it by the wider trajectory team, but that is going on, and I'm really excited to see this burn be successful for the conclusion of the mission.
Absolutely. We're now 17 minutes and 45 seconds away from the anticipated acquisition of signal following today's return-powered flyby burn, which took place about 11 minutes ago. That burn was 3 minutes and 27 seconds and committed us back to a return trajectory headed back to planet Earth, where Orion will complete its 25.5-day test flight mission around the moon and beyond. Now, the last time NASA made a journey around the moon in anticipation of a return home to Earth was during the final Apollo mission in 1972. That crew launched nearly 50 years ago to the day on December 7th, 1972. As part of that flight, Commander Gene Cernan and Lunar Module pilot Harrison Smith walked on the moon, while Command Module pilot Ronald Evans orbited above. The crew splashed down on December 19th, 1972, and completed 3 spacewalks during their mission. And during Apollo 17, they orbited the moon 75 times. Now less than 15 minutes until we expect to regain communication with the Orion spacecraft. If you're just joining us today, 13 minutes and 30 seconds ago, the orbital maneuvering system on board Orion fired for 3 minutes and 27 seconds, propelling the spacecraft around the moon and placing it into a trajectory ahead of a return back to Earth. Orion will splash down on December 11th, completing a 25.5-day uncrewed test flight in which it broke the longest distance from Earth by a human-rated spacecraft meant to return back to Earth. At its furthest point from Earth, Orion was 268,563 miles from our home planet. We're about 13 minutes away from our anticipated acquisition of signal. As Orion flies around the backside of the moon, let's take a look back at what has gotten us to this point so far. First up, we start with the Space Launch System launching from Pad 39B at the Kennedy Space Center in Florida. With its sights set on the moon, SLS blasted off at 12:47 a.m. Central on November 16th. You see those 4 RS-25 engines lighting up the Space Coast. You can also see the core stage climb up, as well as one of the 2 solid rocket boosters in this view. And on top of the vehicle is the launch abort system, and of course the Orion spacecraft now behind the moon. This video shows SLS and Orion's climb to orbit from the perspective of a camera on the rocket. It was about an 8.5-minute climb into orbit. You can see the launch pad grow smaller and smaller as the Space Launch System propels Orion into orbit. Following liftoff and the climb to orbit, the translunar injection burn took place. The translunar injection maneuver took place as the upper part of the rocket, officially named the Interim Cryogenic Propulsion Stage, or ICPS, fired one RL-10 engine producing 24,750 pounds of thrust to accelerate the vehicle to more than 22,600 miles per hour, a velocity fast enough to overcome the pull of Earth's gravity and propel Orion out of low Earth orbit to send the spacecraft to the moon. The TLI maneuver precisely targeted a point on the moon that guided Orion close enough to be captured by the moon's gravity. Now, right after that TLI burn, the interim cryogenic propulsion stage separated from Orion, and you do see that here in the video as it drifts further away from the spacecraft. Later that day, we received our first imagery of Earth, as well as completed the first checkout of the Orbital Maneuvering System, or OMS engine. All went smoothly, and that Orbital Maneuvering System engine was used just 17 minutes ago for the return-powered flyby burn, which lasted 3 minutes and 27 seconds. Several days later, on November 21st, Orion performed the outbound-powered flyby burn, also with that orbital maneuvering engine. This is the sister to the return-powered flyby burn. The orbital maneuvering burn sets us up in a trajectory to head out to deep space. The return-powered flyby burn sets us up on a trajectory to return back home. This video shows Orion as it approached the moon for this burn. And as we mentioned in this broadcast several times, Orion has traveled further than any human-rated spacecraft, but in this view here that was taken just shortly before that, you can see an eclipse, the moon traveling in front of the Earth, a view we don't often see here on Earth. And this photo was taken on Flight Day 13, November 28th, when Orion reached its maximum distance from Earth, when it was 268,563 miles away from our home planet. Orion has traveled further than any spacecraft built for humans meant to return back home. And in this video here, you see Orion's solar rays split the difference between Earth and the moon on Flight Day 14. This image is captured by a camera on the tip of one of the spacecraft's 4 solar rays. And just last week, on December 1st, the distant retrograde departure burn occurred, which placed Orion in a trajectory to exit the distant retrograde orbit and head back toward the moon ahead of today's return-powered flyby, which occurred just 19 minutes 15 seconds ago. In this view here, you can see the solar arrays, gimbal, as well as a Earth in the almost center of your screen there. So as you can see, Orion has had a busy journey in its 20 days of the mission so far, but it's not finished yet. We have about 5.5 days to go until splashdown. But today's return-powered flyby burn was the first step in getting us to the splashdown point. That burn commits us to returning home. We anticipate regaining communications with the Orion spacecraft about 8 minutes and 15 seconds from now. You're looking at a view inside Mission Control Houston. This is the White Flight Control Room. The flight director during today's shift and return powered flyby burn is NASA Flight Director Judd Freeling. You do see a few of the console positions looking a little empty. That is because we are in that loss of signal period. This is a great time for the flight controllers here in Houston to grab a quick break. Today's return-powered flyby burn occurred 22 minutes and 45 seconds ago. That burn utilized the Orbital Maneuvering System, or OMS engine, on board the Orion spacecraft. At this time, the Orion spacecraft is continuing to make its way behind the backside of the moon, and we do not have signal with the vehicle. However, we do anticipate connecting with the vehicle now less than 5 minutes and 30 seconds from now. The reason we do not have communication with the vehicle is because when we are behind the moon is blocking the signal to the Deep Space Network. We're now less than 4 minutes away from our anticipated acquisition of signal with the Orion spacecraft, which is currently traveling behind the moon following the return-powered flyby burn. This burn commits Orion to returning back to planet Earth. This return-powered flyby sends Orion close enough to the lunar surface to leverage the moon's gravitational force and swing the spacecraft into a trajectory to return back to Earth. Now, just before the burn began 25.5 minutes ago, Orion did complete its closest approach to the moon, at which point it was just under 80 miles away from the lunar surface. Beginning to see more folks trickle back into the White Flight Control Room as we narrow in on our anticipated acquisition of signal with the Orion spacecraft, which is currently traveling behind the moon. Now 1 minute and 30 seconds away from our anticipated acquisition of signal with the Orion spacecraft. Once we acquire signal with the spacecraft, the team here in Mission Control Houston, namely the flight controllers, will be able to analyze the data that the vehicle is sending back to us in Mission Control. With that data, they'll be able to analyze if the burn was successful. Less than 1 minute away from our anticipated acquisition of signal with the Orion spacecraft. .30 seconds away from anticipated acquisition of signal. And we are standing by for acquisition of signal with the Orion spacecraft. And we do have confirmation of an acquisition of signal on the Deep Space Network in Goldstone at 11:12 a.m. Central. You're getting a view of the lunar surface from Orion's perspective. And we are hearing good confirmation that the burn was as expected. If you're just joining us, Orion completed its return-powered flyby burn, which slingshot it around the moon and committed Orion to a return trajectory back to planet Earth, hearing that that burn went smoothly and as expected. You are seeing a view on your screen of the lunar surface as well as Earth. For Orion, this is not a goodbye, but a see you later to the moon, our nearest celestial neighbor, as we begin to get our first glimpse of an Earthrise coming into frame. In this view, we see 8 billion human lives all existing upon our pale blue dot, our blue marble, our very own spaceship Earth. And after a long journey, Orion is now coming home. From this view, Orion is 1,277 miles above the lunar surface following its return-powered flyby burn, which sent it around the backside of the moon. Orion now has its sights set on home. Orion will splash down off the coast of California on December 11th. Wrapping up a 25-and-a-half-day mission. This is a view from inside the White Flight Control Room here in Mission Control, Houston. The team is being led by NASA Flight Director Judd Freeling. And this view from the Orion spacecraft as it looks to its target, planet Earth, flying over 1,200 miles above the lunar surface. At its closest approach following the return-powered flyby burn, Orion was just 80 miles above the lunar surface. The next time we see such a view, we will be hearing about it from a crew's perspective during Artemis 2. Continuing to hear good performance following today's return-powered flyby burn. The Orion spacecraft is continuing to distance itself from the moon, now over 1,500 miles away from the lunar surface. Throughout the course of the next few days, we will see the distance from Earth continue to grow smaller and smaller. Orion is now 242,000 miles away from planet Earth. The spacecraft is moving at a velocity of 2,150 miles per hour. We're continuing to get some spectacular views from the Orion spacecraft. This view is from one of the solar array wing or SAW cameras on board the vehicle. The vehicle now over 1,680 miles away from the moon. And that small sliver towards the bottom of your screen, that's here, that's home, that's us. And that is where Orion is headed next. And with today's return-powered flyby burn now complete, and Orion having completed its closest approach to the moon at a distance of 80 miles above the surface, that will wrap up our coverage for today, but we'll continue to post daily updates about the mission on the Artemis blog at blogs.nasa.gov/Artemis, and we'll also be posting updates on our social media accounts. Later today, we'll have a briefing at 4 p.m. Central where representatives from NASA will discuss today's return-powered flyby, which we hope you'll tune in for. And we'll also be covering Orion's re-entry into Earth's atmosphere and its splashdown live on air next week. But until then, this is Mission Control Houston.
Studying in the UK has been one of the greatest opportunities of my life.
I've been given the chance to meet and speak to influential people.
My professors are genuine experts in their field and passionate about their subject.
I've had a lot of hands-on practicals and learned how to develop my own thinking.
I've had the opportunity to discover new perspectives.
I have access to world-leading research and facilities.
Anything is possible
when you study in the UK.
पाकिस्तान में हर 2 में से 1 बच्ची तालीम से महरूम है। एक मजबूत माँ ये बदल सकती है। आए सराहें उन माँओं को जो खुद इम्तिहानों से गुजरकर अपनी बेटियों को पढ़ाती हैं।
आयशा जल्दी करो।
कहते हैं 5वीं पढ़ ली, अब और कितना पढ़ाओगी? पूछते हैं इसकी पढ़ाई के पीछे और कितनी मुश्किलें उठाओगी?
अम्मी, ये गाड़ी में रह गया था।
सोचते हैं पढ़ाओगी तो फिर घर कैसे चलाओगी?
दूध पी ले। अम्मी बस 2 मिनट।
इसको पढ़ाने से, इसको सिखाने से तुम क्या पाओगी? खुद को कितने इम्तिहानों में डालती जाओगी?
वो ये नहीं जानते कि मैं इम्तिहानों से गुजरूंगी तो मेरी बेटी आगे बढ़ती जाएगी।
जब माँ करती है इम्तिहानों का डट के मुकाबला तो ही बेटी पढ़कर मजबूत बनती है।
बल्कि लाइफ टाइम एजुकेशनल स्कॉलरशिप हासिल की है बहुत ही होनहार आयशा अहमद ने।
बेटियों को पढ़ाना पूरे पाकिस्तान को पढ़ाना है। तो आए बच्चियों के आलमी दिन पर लाइफ बॉय शैम्पू और TCF के साथ मिलकर बेटियों को पढ़ाने का अहद करें ताकि बेटियां मजबूत बनें और पाकिस्तान आगे बढ़े।
Okay, hello everyone. Well, thanks for joining me here today. We are going to be talking about getting to the fundamental theory of physics. Now, I never expected this. If you'd asked me even last fall, I would have said that I have an idea, but I don't know if it's going to work. Tell you kind of here where we're at so far. I mean, it's been a long road for me. I first got interested in physics nearly 50 years ago now, and I started doing physics when I was a kid. I used to do physics for a living, but as many of you may know, I've spent most of my life sort of pursuing the idea of computation, which is a really powerful idea, and it's actually what's leading us to the physics we'll be talking about here today. And I've sort of spent my life alternating between doing science and doing technology with the idea of computation. And one of the things that happened as a result of that is that back in the 1980s, I started studying this kind of universe of simple programs. And I discovered this amazing thing, that even when the programs that you're looking at are very simple, even when the rules you set up are very simple, the behavior you can get can be incredibly complicated. And that kind of discovery sort of put me on a path that led to all kinds of things. And it got me wondering about whether maybe that's how physics works. Maybe there's some very simple rule underneath everything that exists in our universe that leads to everything we see. And I kind of had a definite idea about how this might work back in the 1990s. And I started working on it. And I actually wrote about 100 pages about that idea and its consequences in this, well, they're here, this big book that I wrote back in 2002. And actually, in the end, as I now realize, I got really close to figuring out what we've now figured out, but I didn't figure it out back then. And I ended up hibernating this idea for a long time and doing things like Wolfram Alpha and Wolfram Language and so on. And I always wanted to get back to this, and I was always kind of thinking about it. And then a little over a year ago, I had kind of a little idea that got me a little bit more enthused. And then two young physicists, Jonathan Gorard and Max Piskanoff, who came to our annual summer school, got really excited about this and said, you have to work on this, and we're going to help you do it. And that's what really got me started again. And we started really working on this last fall. And it was a totally amazing experience because, as I say, I've been interested in physics for 50 years. And there are all these things about physics that I've known about quantum mechanics, about relativity, all these kinds of things. And suddenly, it all started falling into place. It all started making sense. We started realizing how this stuff really works. And it was just great. And I want to try and tell you a little bit about that experience here today. Really, the thing that I think is most spectacular about it is how beautiful the whole thing is, how all these different pieces fit together in this really beautiful way. And I should say that what we've done would not in any way be possible without sort of all of the achievements of physics so far. I mean, basically what we're doing leverages particularly the two great developments of 20th century physics, general relativity and quantum field theory. Without those, we wouldn't be able to get to where we are. And and the other thing I want to say is that one of the things that's been really neat is that there have been lots of modern developments in physics and mathematics. And it turns out that an awful lot of those seem to fit beautifully together with the things that we figured out about physics. And so it isn't one of these cases where it's like something new is coming in, you throw out all the old stuff. It's, no, we have a kind of a new foundation, but all this other stuff that's been being worked on, it fits in beautifully. And I think it's going to be something very, very wonderful to see. Well, so I want to tell you all about this here today and hopefully get your help in finishing this job. Of course, the timing of this is totally weird because we're right now in the middle of this terrible pandemic. I mean, our company has been off curating data and doing modeling and helping where we can with pandemic kinds of things. But I figured that, among other things, while we're all stuck at home, people might enjoy some physics. And there's kind of a strange historical resonance with all of this, because back in 1665, there was also a plague, and a chap called Isaac Newton had to leave Cambridge University and go hang out at home. And while he was doing that, he kind of figured out the basic ideas of calculus and his theory of gravity. Well, we may not be able to match old Isaac, but while we're stuck in this pandemic, maybe we can all figure out physics. All right, so let me show you what we have so far. So what I'm going to do here is I'm going to go through sort of a basic outline. There's a lot to say, but I'll go through a basic outline. Then we'll have a Q&A here today. Then tomorrow we'll be doing a more technical Q&A for physicists and mathematicians, followed by one talking about more sort of philosophical implications. Then on Thursday we'll do a Q&A for computer science folks. And then we'll be starting kind of live streams of actually doing this project. We really want to make this as open a project as we can. And as part of that, we'll be live streaming our kind of working sessions and our discussions with other people about this project. And we hope lots of people can participate in those. All right, well, let me get started really here. Okay, let's go here. And start. All right, so let me start off. This is our website, and you can find most of the stuff I'll be talking about here today somewhere on this website. There's probably about 1,000 pages of material on this website. Let me just point you to a few pieces of this, which maybe will be useful. First of all, there's an announcement here. This is kind of a basic outline. It was supposed to be a short announcement. It turns out it's about 60 or 70 pages, but it's kind of an outline of what we're doing here. Oops, I'm being told I'm not sharing my screen, so let's check that. That is bad. Hold on. Boom. There we go. Okay. Well, let's start that again. So I was saying, this is this is our main website that just went live. There's about 1,000 pages of material here, and let me go through a few pieces of this. Here's some. Let me see here. Okay. So there's some our main announcement. There's kind of another piece that I've written, which is kind of about the backstory of this project, kind of how we got here. Then there is kind of technical introduction that I've written. It's kind of describes in more detail kind of how the models that we're discussing work. Then there are an area for technical documents and related material that includes a couple of papers by Jonathan that for people who are kind of equations first readers, particularly professional physicists, I would encourage you to check out some of Jonathan's work here. Then there is an area here of software tools. One of the things we're doing is to make all the tools for doing the things that we've been doing completely available. They're available today, and you should be able to run them in Wolfram Cloud or anywhere where you're running Wolfram language, and that's a way that we hope people can start to participate in this. I'll be talking more about some of these other things later. This is a registry of notable universe models. We'll be talking about that a bit more later. There's also, I'd like to point you to the Q&A. We've answered some of what we think of as the most obvious questions here. As questions come in, we'll try and answer more of them, but I encourage you to check that out also. Okay, well, let's get down to business. How do we think physics basically works? Well, here's a kind of a pictorial outline of things, and this looks kind of complicated. I guess that might be because our universe is ultimately kind of complicated, but this is a lot simpler than that this is kind of showing way down below underneath our universe. So I'm going to be talking about different parts of this. I'm going to be talking about how we start from this very simple kind of rule, how we build up a structure that represents space in our universe, how we understand how time works, how we derive from the properties of space and time relativity, special relativity, general relativity, the theory of gravity. I'm going to be talking about how the different paths that you can follow in applying this rule correspond to the different paths that can occur in quantum mechanics, and the way in which one gets this sort of entanglement of states in quantum mechanics, and how that emerges in these models. And in a sense, one of the most spectacular things that happens is that it turns out that relativity and quantum mechanics are in some sense the same idea in these models. There's a sort of complete unification of the notions of relativity and quantum mechanics, which is one of the most beautiful things, I think, that comes out of this. And sort of in the middle of a bunch of those things are things about black holes and the quantum mechanics of black holes. Let's see, people are asking for me to zoom in a bit here. I think, unfortunately, if I zoom, I will, well, okay, here we go. I encourage you to just look at this for yourself on the web. This is under the visual summary on the website. Okay, well, let's start in on how this stuff works. So the thing that we're interested in is to figure out if there is a rule underneath the universe, what might that rule be like? And if the rule is going to be at all simple, we pretty much know that nothing that we're familiar with in the universe is going to be immediately evident in that rule. We're not going to be able to see that the rule has a 3 for the number of dimensions of space. We're not going to be able to see that the rule has some case for some particular detail of the properties of the electron and so on. That rule has to be something that sort of packages everything about the universe into some tiny bundle from which all the things that we observe must emerge. So what I realized long ago is that we need that rule to be as kind of minimal and structureless as possible. And we need to have something that sort of allows the possibility of everything that we see in the universe emerging. Now, one of the things that is sort of a basic feature of this rule is we don't get to have any notion of space intrinsically in this rule. And so we have to kind of make space out of something. And in the end, one of the things that's sort of a first surprise is the idea that happens in these models that space is something discrete. Space is made out of a bunch of discrete points that are kind of going to be knitted together. And traditionally, for the last couple of thousand years, actually, people have kind of assumed that space is somehow a continuous thing, that you can just say, I'm going to pick any position in space. It'll be specified by some precise triple of numbers, for example. And that's how we define that we can do that. We can pick any possible position in space. What happens in these models, among other things, is that that's no longer possible. And instead, we're making space out of these discrete elements. And one of the other things about these models, I said it's very minimal, very very little that gets put in from the beginning. In a sense, everything is just space. And all of the features that we are familiar with about matter and elementary particles and all these kinds of things ultimately will emerge as features of space. Okay, so let's talk about what the rules for kind of doing things in might look like. Okay, so what we're going to be talking about are rules which we can represent as rules for hypergraphs, or we'll talk about those in a minute, but we can think about them as rules for graphs or networks. And so for example, we might start off by saying, let's imagine that we have some structure like this, and we have these elements. We're just numbering them 1, 2, 3, 4. And then we have some rule that says how we're going to update this by just looking at the different patterns of elements here. What are we going to do to this structure? And it's sort of an embarrassing thing to admit, but the basic idea for how these rules work is something that is sort of also the foundation for kind of the symbolic programming that is the foundation for Wolfram language and is actually the foundation for pretty much all of the practical things I've done in computation for the last 40 years. And the embarrassing thing is that I didn't realize that sort of the essence of that symbolic programming idea was exactly what's needed to understand how to build physics out of. And I was working on sort of a slightly different way of setting this up. But the essence of that idea turns out to be the essence of the idea that it looks like we need for physics. So this is just an example of essentially a rule. This is just a sort of more algebraic representation of the thing I was showing earlier, this rule that tells us how to replace one sort of structure in our graph with another structure. Okay, so let's say we start off with some graph that looks like this. Then let's just try applying that rule a few times. This is what we get. So it's the beginning, then we apply the rule, we apply it again, and eventually we're getting something like this. So this is kind of the story that I first learned in the 1980s, that even when the rule is very simple, the behavior and the structure that you get can be complicated. So this is an example of what you get after just running maybe 10 steps or something with that particular underlying rule. So you can say, so what's in the end going to happen is we're going to run this rule maybe 10 to the 400 times, or a rule like this maybe 10 to the 400 times, and that's going to build our universe. Now, I will say at the outset, we don't yet know exactly what the right underlying rule is. It's going to turn out that an awful lot of what shows up in physics, and this is one of the big surprises, is quite generic and actually quite independent of the details of this underlying rule. So we can already derive lots and lots of physics without knowing this final ultimate underlying rule. One of the things we want to find is what that final ultimate underlying rule is. So if we ask ourselves, well, what kinds of things happen with different rules? Here are just a few examples of things that happen with some of the simplest possible rules. And what we're anticipating is that when we look at enough of these rules, eventually one of them will turn out to be the rule for our particular physical universe. I'm going to make a little footnote to that. I'll explain later why, in a sense, there can be many different rules that all represent our universe, but we'll get to that in more detail later. In a sense, this sort of process of looking at all these rules and seeing what happens, it's sort of a very zoological thing. It's very, it's as if you're looking at all these different possible creatures in the computational universe, and you're trying to find the one that actually corresponds to our physical universe. But so all kinds of different behaviors can occur, this is what we're interested in looking at. Okay, so first question is, how do you get something like space as we know it? So the basic idea is that when you're looking at the kind of large-scale limit of one of these structures, after it's grown for a very long time, you'll have something which, to a high degree of approximation, seems like the space that we're familiar with. So it's kind of an analogy that one's very familiar with, that we've known about for maybe 150 years, although it was guessed even much before that something like a fluid like water that seems to us continuous, it seems to sort of flow continuously. We actually know that ultimately it consists of a bunch of discrete molecules bouncing around. And I think the same thing is essentially what's happening in space, that space is just a bunch of discrete points, but on a large scale, it seems to us like something continuous that we can apply mathematics like calculus and so on to. Okay, so how can we see that more precisely? Let's take a look at a particular very simple rule. It's just one of these specific rules, and this is the first few steps of what it does. And if you keep going for a while longer, you'll discover that you can start seeing it here. It's kind of knitting this structure. Keep going for a while longer, you'll find that it knits a structure like this. Keeps going, keeps knitting this structure. Well, when we look at the structure, we can kind of make a reasonable guess that in the end, this is going to be kind of like ordinary space. It's going to be like a plane that's just a mesh that corresponds to sort of two-dimensional space. And that's, so that this particular case is very easy to see how the thing produces something that's kind of like space. So, but things aren't always that simple. Here's an example of another rule. This makes a structure like this. Understanding the limit of this is more complicated. Here's another one. This makes a structure like this, which we can again kind of recognize as something that's a little bit like our sort of traditional mathematical object with a two-dimensional surface or something. Actually, if you project that into 3D and kind of fill it in, it'll make a structure that looks like this. Okay, so what we've got underneath is just this discrete collection of points, and all we know is which point is joined to which point. We don't know, there's nothing that intrinsically tells us that the thing should lay out as a structure like this. All we know is by a hyperedge. That's just sort of a detail of how we're building things, but it's why we'll refer to the structure that we think limits to physical space as being the spatial hypergraph. Okay, so let's say we want to analyze what's happening in a system like this. How would we do that? Well, one question would be, given that we have a structure that looks like this, and we look at it with a very large number of points in it, what dimensional space might this correspond to? Well, actually, there's a pretty simple way to determine that, and here's how it works. And there's a little bit of mathy stuff, but it's not too bad. So if we think about a two-dimensional grid, and we just say, let's start at a point in the middle of this two-dimensional grid, and let's keep going to points that are one step away on the grid from the points we've already got to. Let's keep growing that structure and see what we get. Well, one of the things you'll see here is if we just count how many points we got to after we went, let's say, r steps, we'll discover that the number of points we got to is about r squared. So that squared in the r squared, that 2 in the r squared, that 2 is the thing that represents the fact that this is behaving like two-dimensional space. It's behaving like just a grid on a plane. If we do the same thing in a 3D, in a graph that's made to correspond to a 3D grid, we'll find out that we do that same computation, we'll find out that the number of points we get to is about r cubed. So in other words, that cubed is what tells us that we've got something that is behaving like three-dimensional space. Okay, well, we can do exactly the same thing in one of these structures here. We just start from one point and we keep going to points that are one more step at each one of these away from the points we got to already. And then we can ask the question, if we do this, how many points do we reach after we've gone r steps? Okay, and we can start plotting that, and it's a little bit complicated because there's sort of multiple things happening. We're kind of evolving the structure, so the structure is getting bigger, and we're also asking for these kind of balls of points that we're looking at. We're asking what happens as they get bigger. But anyway, when we do that, we'll find out these are just curves that represent the essentially the logarithmic difference of growth. Well, its growth rate. It represents it sort of fitting that exponent. And so what we see here is that exponent is roughly fit by about 2.7 or so. So what that means is that structure that we had, this thing here, in the limit, this thing is behaving roughly like 2.7 dimensional space. It's kind of like it's not quite three-dimensional space. It's more like the kind of thing you would find with fractals and so on, where it is behaving like a fractional dimensional space, but it's behaving like a space with a definite, albeit fractional number of dimensions. If we go back to something like this, and we do that same test, we'll find out that in that case, when we measure it, this thing indeed behaves like it's two-dimensional space. And if we do the same thing for something like a fractal, we can measure that, and we'll find out that it behaves like in that particular case of that particular fractal, it's about a 1.58 dimensional space. Okay, so this is kind of giving us an idea, how do we work out the dimension of space? Well, another question would be, okay, we've got space, but our universe isn't just space, it's got a lot of stuff in it. It's got a lot of particles like electrons and photons and all those kinds of things in it. And so one question would be, what are those things like particles? So the basic picture is this, that there's sort of a background of activity in space where this thing is sort of bubbling around and lots of connections are changing here. But there are certain pieces of this network that have a certain, at least local stability to them. And those things are the things that correspond to particles that we're familiar with. So as an analogy for that, we can say, imagine this network was just planar, was just everything could be laid out in the plane. But imagine that somewhere in that planar network, there was a little piece that wasn't quite planar. That might correspond to something like a particle in that network. It's a thing that's sort of locally stable in the network and can move across the network and sort of keep its identity. And that's how we think particles work. We haven't actually found particles in specific, in the more complicated rules here. And that's one of the things that we hope to start working on in the next few weeks. All right, so first thing about space is to know what dimension it is. And for our universe right now, we want that we know that number is roughly 3. As we'll talk about, maybe one of the things that comes out of this theory is that the dimension of space might not be exactly 3. There might be variations in the dimension of space that might be associated with phenomena in cosmology. It might be that in the early universe, the dimension of space wasn't exactly 3, but may have been much larger than 3. Talk about that a little bit more later. Okay, so one feature of space which was discovered, comes out of the general relativity invented by Einstein in 1915, is the idea that space is not just a flat three-dimensional thing, it's something that has curvature as well. And in fact, we can understand the phenomenon of curvature in these networks. Here are examples of networks that grew from simple rules. And we can kind of get some sense as these networks are laid out here that there's some kind of curvature to the space that corresponds to these networks. Well, that criterion that I told you for working out dimensions of space, you can use a similar criteria for working out curvature. And just to mention how that works, you know, when you might think the area of a circle is pi r squared, but if you draw that circle on a sphere, its area isn't exactly pi r squared. There's a correction that depends on the fact that it is being drawn on a curved object. And that we can kind of key into that correction. So we can work out actually that when we do this thing about saying sort of how big is the ball, how many points do we get to when we go a certain distance in our system, that will end up not being something which in this plot looks like it's just sort of flat two-dimensional space. Instead, this thing will have a variation, and that variation corresponds to curvature. And we'll see all sorts of features of that curvature. One thing I might mention, sort of from a mathematical point of view, is that what comes out in these models immediately is that what matters to the sort of growth rate of number of points is a thing called the Ricci scalar curvature, which turns out to be exactly something that shows up in general relativity. But one of the features of curvature is when a space is curved, it means that the shortest distance between points is no longer an ordinary straight line. So if you were just on this flat space, the shortest distance would just be these straight lines. On a sphere, these so-called geodesics, these shortest distances, they kind of bow out like this. This is a space of negative curvature where the geodesics get squashed together. Well, we can look at exactly these kinds of things in our systems, and we can, and this is and well, the thing. So by the way, in Einstein's idea of general relativity, gravity is associated with the fact that when when things travel, like a laser beam, for example, would travel in what it thinks is a straight line. But because space is curved, that straight line to it is not really a straight line. And that non-straightness is what is associated with the effect of gravity. And we have exactly the same phenomenon. And in fact, we can go ahead and work out the effective equations for these for what happens with these geodesics and so on. And it turns out that the equations one gets for the limit of what happens with these geodesics in our space that's created just from these underlying rules being applied to create this larger and larger spatial hypergraph. It turns out that the equations that govern the behavior of these geodesics are exactly Einstein's equations. So to begin with, a little bit of more technicality. To begin with, what we're talking about so far is the vacuum Einstein equations, the equations that govern essentially the curvature and structure of space itself. Okay, so so that's a little bit on how space works. Another big thing about our universe is time. I was sort of describing this as these spatial hypergraphs, they just grow, but they grow in time. How does that time thing work? Well, one feature of the sort of traditional approach to physics is this idea of space-time, the idea that somehow space and time are in some sense the same kind of thing. And that's an idea that kind of gets a lot of special relativity is very much involved with space and time being sort of the same kind of thing. But in these models, space and time aren't intrinsically the same kind of thing. And space is this extent of the spatial hypergraph, and time is the kind of inexorable computational process by which that spatial hypergraph evolves. And it will turn out, as I'll explain, that even though space and time in these models are fundamentally very different kinds of things, it will nevertheless turn out that all the phenomena of space-time emerge and one gets all of the standard results of relativity and so on. But at an intrinsic level, space and time aren't the same kind of thing in these models. And if I were to pick sort of one potential wrong turn in the history of physics, it was probably about 100 years ago when people started saying space and time really are the same kind of thing and not considering the possibility that they should be thought of differently. It's something that's come out of sort of our computational paradigm, that time is this thing that corresponds to sort of the process of computation, and space is something different. Okay, let's talk about time. So when I showed this sequence of different steps in the evolution of this graph, I was a little bit cheating, because what I really should have shown is every individual little update that gets applied by that underlying rule. So this is a possible set of such updates, showing in purple the parts of that got applied. So what I was actually showing were these sort of complete steps after sort of every update that could have been applied to this graph had been applied. But this is kind of looking underneath, looking at every possible update that might have been applied. Okay, so here, sort of the progress of time is about the applying of these updates. But now there's a very important thing, which is this picture is not the only picture that I could make about how these updates are applied. When we're given the underlying rule, there can in general be many different places in this graph where the update could be applied. So how does that work? Well, actually, what we can think of is this whole graph of all the possible updates that could be applied. So here's the starting state. This is one update, goes to here. A different update goes to a thing which actually looks similar, but the arrows will be different here. We keep going, we'll get to these different structured states. And if we keep going again, we'll get to yet more states. Okay, so maybe it's sort of a spoiler here that this sort of branching is going to turn out to be what gives us quantum mechanics. But for current purposes, what I'm explaining is that the sort of progress of time is down the page here. And what we're seeing is that there'll be a progression from one spatial hypergraph to another, and that corresponds to the progression of time. If we continue this graph longer, well, this is a version of this graph where we didn't arrange it so that it sort of explicitly goes down the page. This is just showing the relationship between these different spatial hypergraphs. Okay, well, let me, to sort of explain how this works. Okay, so it's going to be a little bit, we're going to get to what we call causal graphs, which are a very important concept, and they're a bit easier to explain, not in the context of spatial hypergraphs, but in the context of just rewriting strings of characters. So think of it being as like being in a sort of find replace text editor. You've got a big string of text, and you're told anytime you see an A, you can replace it with BBB. Anytime you see BB, you can replace it with A. Okay, so the question is then, what happens if you run your text editor sort of in all possible ways? So this is what we call a multi-way graph of what happens. So we might start with an A that can only give BBB, but then BBB could give one possible transformation as it gives AB, another transformation it gives BA, and it keeps going from there. Okay, and so we end up with this whole network of possibilities. Okay, so that's analogous to the network of possibilities I was showing you before for spatial hypergraphs, but it's a little bit easier to see in the case of strings. Okay, so we can look at that in a little bit more detail. This shows what we can think of as the updating events. So this starts with an A, and then this is the sort of updating event that says A goes to BBB, and there's more updating events. So this is showing kind of the network of states and events, showing sort of how things can progress through time, in effect. Okay, so now I'm going to make this even a little bit more complicated, because one of the big questions here is, what can happen before what? And we can think of these updating events as being like, well, you can think of them sort of computer science-ly like functions, and they have certain inputs. And a particular updating event can only occur if all its inputs are ready, in some sense. You have this kind of ordering of what can occur when, based on when its inputs are ready, so to speak. We can draw that here by adding these causal relationships. So they're saying this particular thing depends on this having happened because it needs that in order to get its input. And so down here, there might be something that needs this to have happened in order to get its input, and so on. And so all these orange lines represent the causal relationships, the what thing needed to get its input ready from something that happened before, so to speak. Okay, so we can then, let's now get rid of the states and just talk about what we can call the causal graph. That is the graph that represents the causal relationships between events. This says an event here, this event here could only happen after this event here. This event here can only happen after this event here. This is a graph of causal relationships. Okay, and this is going to turn out to be sort of a critical thing in understanding a lot of what goes on. Let me show you, so if I kept going a little bit longer and I didn't lay it out, sort of starting from the first event, I might get, this might be the causal graph of relationships between different events, the threads of causality that join those events. Okay, now let me explain something, a very important idea here, which is the idea of what we call causal invariance. So one of the questions is, we've said there are all sorts of different updates we could do, and there are lots of different orderings in which we can apply those updates. But it turns out, for many kinds of underlying rules, it doesn't matter what order we use. So long as we respect this causal graph, we can do the updates in any order we want. Okay, let's show an example of causal invariance in action. Essentially, what causal invariance, this is for a particular rule that is a rule that takes our string of characters and just two at a time sorts them. So it says that BA should get turned into AB. That's all it's doing. And this is showing, starting from BBB AAA, this is showing all the possible ways that BBB AAA can get rewritten with that particular rule. And we see these various events that can occur and so on. Okay, so there are all kinds of different things that can happen. We can wind up with BAB, AAB, we can wind up with ABB, ABA, but in the end, we're always going to get the same answer. In the end, we're always going to get a sorted string. Doesn't matter what sequence of states we went through, we'll always get to the same answer in the end. And that's the essence of causal invariance. It's actually a property that has been studied in mathematical logic and other places. It's sort of re-emerged many times under many different names, sometimes called confluence, has a variety of different names, the Church-Rosser property, all sorts of other things. There's slight technical differences between all these different things, but they're basically the same idea. How would you know that this idea exists? If you've done algebra, you might know that when you are doing something like expanding out some polynomial, you can say, well, I'm going to expand this set of parenthesized terms first, and then I'm going to do this one, or I'm going to do it in the other order. But in the end, it doesn't matter what order you do it in. That's because that kind of algebra has this confluence or causal invariance property. And some of these rules that we're looking at also have that property. So this particular sorting rule has that property. Okay, so what? Well, the big so what is then what that's saying is there are these different possible sort of paths of history, but it doesn't really matter in some sense which path of history we choose. We're always going to sort of get the same behavior in the end. Okay, so for example, for this particular thing, we can look at what the causal graph that it makes is. Its causal graph is actually very simple. It just looks like this. Let's look at how this works in sort of actually operating on the original string. So here we have a fairly long string, and each of these yellow boxes represents an event. It represents a rewrite of BA gets turned into AB. So this is a particular choice for how we can do that sequence of rewrites. I can show you what the causal graph associated with that. Special relativity is not usually something that one imagines deriving. It's something which, in a sense, is a consequence of sort of axiomatic features of the way physics is set up: constancy of the speed of light, independence of inertial frames, these kinds of things. But in these models, we get to actually derive special relativity. It might not be true in these models, but it is true. It is a consequence of causal invariance and of various kinds of limits and intrinsic randomness properties and things of these models that one gets special relativity. So let me show you roughly how that works. So let's look at a simple causal graph. Here's a simple causal graph that has a bunch of events joined in these simple ways. So let's imagine that the important thing to say is in special relativity, one of the sort of big innovations was being more realistic about what an actual observer of the universe can tell is going on. So if we sort of look from outside the universe, we might be able to see all sorts of things. But as an observer embedded in the universe, operating according to the same rules as the universe, there are limits on what we can tell. For example, in the sort of physical case, we can't. Things can only travel at the speed of light, so we can't be aware of things yet that were sort of that happened further away than we have been able to see them based on information from them coming at the speed of light. So there's a question of sort of how do we model that observer? How do we model an observer who is embedded inside the system? And I might say that for the systems that we're looking at here, one of the things you might ask is, if the observer operates according to the same rules as the system itself, what consequences does that have? Let me give you an example of a consequence that have, a rather bizarre consequence. Let's say that we were to set up the universe so only one place in the universe ever gets updated at a particular moment. So what's then happening, it's kind of like a Turing machine in computer science. You have this sort of head that's zipping around the universe, updating different parts of the universe. You might say, that can't possibly be the way the actual universe works. I can plainly see that's not what's happening. The problem is, if you start thinking about it, you realize that you can't see anything until, in a sense, you've been updated. And as this head zips around trying to update different things, it's kind of the causal network that it is producing is one that actually can look pretty much like this, where you can't tell that that thing over there has or hasn't been updated until you yourself have been updated. And so when you sort of put all of that together, you realize that you get this sort of one integrated causal graph in which, in a sense, things to you as an observer can sort of seem to happen at the same time, even though to something sort of outside the universe, you might imagine seeing this head just zipping around doing different things at different times. Okay, so how do we make sort of a model of what that observer is like? The thing an observer will do is to say, okay, I'm going to decide what counts as successive moments in time for me. And so this is mathematically foliation of this causal graph. And this is saying these are the successive moments of time that I, as an observer, am going to decide to identify as this is my definition of time, is going to be the sequence of slices like this. Okay, well, the important thing is, let's see, I think I have a better picture than that. Yeah, here we go. So, right, so let's imagine that our observer is not just stationary, but our observer is moving. Okay, so this is now our moving observer. To our moving observer, that moving observer will choose their kind of foliation of space-time in a different way. If we say, well, what will this be perceived like to an observer, we'll realize that the sort of perception to the observer is of something like this, where the observer will say, okay, I'm just having these sequence of simultaneous things of sort of surfaces of simultaneity, what are in physics called space-like hypersurfaces, the sequence of space-like hypersurfaces, and then this and that, when I make that transformation, my causal graph will seem to me like this. Okay, so what? Well, the so what is that transformation of the causal graph happens to be exactly the transformation that occurs in special relativity. And in fact, we can see kind of, so what's happening here is that even though we might start off from this this just simple rule that's operating according to in this particular way, it produces this causal graph. Once we have this causal graph, when we are entities sort of existing in this universe as part of this causal graph, we will end up perceiving the operation of the universe to be exactly the way that special relativity says it has to be. So one of the phenomena in special relativity that's is time dilation, and time dilation is kind of, as you will we can kind of see time dilation here in my other picture probably. Oh no, that one. If you're moving in space, if you're kind of exploring space more rapidly, time will move more slowly for you. And let's take a look at how that works in these systems. So let's say we've got something like this. This is, so time, the events are sort of occurring at a certain rate here. If we now pick a different reference frame, if we are effectively traveling at a certain speed in space, this is the sequence of underlying events that we'll perceive. And you'll notice that there's sort of, it takes longer to get to the final answer here than it did when we were just sort of stationary and choosing to choose our sequence of time, moments of time differently. And that phenomenon is, in fact, exactly time dilation in special relativity. And the reason, okay, so why does this all work? The reason this works is because of causal invariance. What causal invariance implies is that even when we are picking this different reference frame that corresponds to going at a different velocity, even when we pick a different reference frame, it will still be the case that the causal graph that we get out from the system will be the same, and that's a consequence of causal invariance. And so causal invariance implies special relativity. Now, the real situation is a little bit more complicated than I've showed you. The real situation, this is a slightly more realistic causal graph, still not really as wild as they come. But this is sort of the foliation of this more realistic causal graph, and it's the fact that this causal graph has this property of causal invariance that implies the validity of special relativity. So again, even though space is this whole thing that's built up from this extent of the spatial hypergraph, time is just this sort of computational progression of applying update rules. It's still the case that when we look at what we as observers inside that universe perceive, what we perceive as the causal graph, and when there is causal invariance, that has the consequence that what we see will satisfy the rules of special relativity. In a sense, the causal invariance is what leads to the independence of reference frames that special relativity talks about. All right, so that was the first. I mean, I think it's a big deal. I knew this in the 1990s, actually, that from models like this, it was possible to derive special relativity. Let me tell you something I didn't know at that time, which is what things like energy are. So and it's really surprising to me that it's possible to say this as simply as it'll be possible to say it. So I'll just say what the final statement is. Energy is the flux of causal edges through space-like hypersurfaces. And so what does that mean? It means when we look at this picture, I made these slices here. These are the so-called space-like hypersurfaces. These things here, these are the causal edges. And the statement is the energy, if we look at some region of the universe and we ask how much energy is there in this region of the universe, the answer will be the amount of energy that's there is basically the density of these causal edges that slice through these space-like hypersurfaces. And in fact, so that's in this model, that seems to be what energy corresponds to. So momentum, for example, corresponds to the flux of causal edges, not through space-like hypersurfaces, these horizontal surfaces, but through what are called time-like hypersurfaces, which are the sort of orthogonal surfaces here. So the momentum corresponds to the flux of these edges through time-like hypersurfaces. Well, now one of the things that comes out in relativity, that's sort of an assumption in relativity, is that space and time have the same relativistic transformation properties as energy momentum. In this model, that is derivable, and that comes about because of this fact that energy represents these slicing through space-like hypersurfaces, momentum slicing through time-like hypersurfaces. When you work it out, you'll discover that that it implies the same special relativistic transformation properties for energy momentum as for space and time. Okay, so another big thing in the world is mass, and you can understand mass, rest mass, in terms of this as well. Rest mass is a little bit more complicated to describe, but it is essentially it relates to kind of the part of energy that kind of does not correspond to communicating with different pieces of the spatial hypergraph. It's the part of the energy that sort of has to do with a single part of the spatial hypergraph going sort of being rewritten in place, so to speak. That corresponds to mass. So actually, I think I even mentioned in the announcement post, and I mentioned in more detail in the technical paper, and I think Jonathan mentions in even more detail in his technical paper, that means from those definitions of energy and mass and so on, we can simply derive, for example, E equals mc squared, which again is quite remarkable because that's not something that has been derivable in physics before. That's something that really comes from the sort of axiomatic assumptions of relativity. But in this case, it's actually derivable from sort of the underlying structure of these models. Okay, so that's okay. So I should mention another thing. The Einstein's equations for gravity, the way Einstein's equations work, they say this is kind of a version. Oh, actually, that has a okay. It's a version of Einstein's equations that talks about the curvature of space. That's what's on the left-hand side, equals this thing here, the energy momentum tensor, that has to do with energy and momentum in space. Well, since we think we know what energy momentum is, and we think we know what curvature is, we should be able to derive this equation, and indeed we can. And indeed, this equation follows as a result of causal invariance. This equation is an inevitable consequence of causal invariance plus a few other kind of mathematical features of these models. In fact, to say how it works roughly, the main other assumption is that sort of at a microscopic level, the sort of individual rewrites that are happening occur in a kind of random way. Now, they're not really random at all. They're completely determined. But when we look at one of these things, it looks to us random. It's the same thing that happens, I don't know, in the digits of pi, for example. The digits of pi have a completely determined sequence, yet when we look at those digits, they seem for all practical purposes random. And if we do statistics on those digits, they'll come up as being just like a random sequence to all of our statistical tests. Well, the same thing happens for the points in space. At a very small scale, the points in space are completely determined how they all work and how they're all connected, but they seem for all practical purposes random. And that effect of randomness allows us to use various kinds of statistical arguments that allow us to derive sort of the continuity of space and so on. And essentially, we need that kind of intrinsic randomness generation. We need causal invariance, and we need one other crucial fact. And the other crucial fact is that the universe is finite dimensional. The universe is not zero dimensional, and it's not infinite dimensional. And if we put those facts in, then we can derive Einstein's equations. And it's actually analogous. The derivation is actually surprisingly analogous to the derivation of the equations for fluid flow from knowing about microscopic dynamics of individual molecules. And for sort of the same reasons as it doesn't matter what the individual molecules look like, you still get the same fluid equations. It doesn't matter the precise details of the underlying rule here, you still get Einstein's equations. So kind of another big deal. I mean, I kind of knew this, well, I knew at least the left-hand side of this back in the 1990s, that was derivable from models like this. But since I didn't know how energy momentum worked, I couldn't really get the right-hand side properly. Okay, so that's that. So let me talk a little bit about the other things in the universe, so to speak, and then I'm going to talk about quantum mechanics after that. So let's talk a little bit more about the universe. So one question is, when we look at the, so when we look at the spatial hypergraph and its evolution, it can do all kinds of things. Here's one of the bizarre things that can happen. A piece of the spatial hypergraph can break off. It's like we've got the universe, it's all going along just fine, and then a piece just breaks off. Once it's broken off, it can never communicate again. It's stuck. It's a disconnected piece of space-time. Okay? Well, what does that remind us of? That reminds us of black holes. And indeed, in these models, it's pretty natural to form black holes. This is a causal graph. And this causal graph says you start here and everybody's communicating, everybody's going back and forth. But then, well, then it splits. And this part of the causal graph splits off from this part of the causal graph. This is the inside of a black hole. This is sort of the outside of a black hole. So that becomes a natural thing that happens in these models, the formation of singularities, and a lot of the phenomena. Essentially, if you are familiar with general relativity, these causal graphs of ours are very much like the causal diagrams of general relativity, but they are now derivable from something much lower level. So if we look at what might our universe be like, these are just sort of three examples of different kinds of rules. This is one that forms a lot of disconnected pieces that these pieces are not space-time disconnected, but they are causally disconnected. So they will act like black holes. This one is a weird universe where things don't communicate much with each other. This is more like sort of this is way too simple to be our actual universe, but this is more like ordinary space. So now one question would be, in the very early universe, what might it have looked like? And one of the things that comes out of these models is the idea that the very early universe could have been much higher dimensional than our current universe. And that turns out to to solve a bunch of problems about inflation and cosmology and so on, the idea that you have a universe that starts very high dimensional so that everything can easily communicate and then only gradually becomes more like three-dimensional. Now, by the way, when I keep on talking about dimensions changing and so on, there isn't a lot of good math around how to do that. Typical studies of the way things work are based on spaces of fixed dimension and typically integer dimension. And so, for example, essentially all of calculus is built on the idea that one's looking at sort of continuous spaces of integer dimension. And so in order to really, one of the things that we need is to figure out essentially a generalization of calculus that works for these fractional dimensional spaces, and that also works for spaces which can change their dimension, and which can work for things, bizarre things, like it could be the case that it's possible to reformulate general relativity, not in terms of curvature of space, but in terms of dimension change in space. So those are some of the kinds of strange things that can happen. Let me mention one other thing while I'm talking about structure of space, and let's talk a little bit about particles again. So, you know, I've studied cellular automata a lot. This is an example of a cellular automaton. A cellular automaton, unlike the models we're using for physics now, where there's just a bunch of points that are all connected in arbitrary ways, a cellular automaton has a very rigid grid. It's just a rigid grid of cells. Each cell is, for example, either black or white, and there's a rule that updates the color of each cell based on its neighbors. So it has a very rigid notion of space and time. It doesn't have dynamic emergent space and time. It's just you put it in from the beginning and then you see what happens. But it's easier to actually run simulations and so on. There's a particular cellular automaton, rule 110. And one of the features of this cellular automaton is you can see that it has these kind of like persistent localized structures that develop in the cellular automaton. And these behave very much like particles. They interact, they have various rules for colliding, et cetera, et cetera, et cetera. This is kind of our, this is a kind of an analog of the particles that we might see in these networks. And as I mentioned before, we don't yet know in detail how that works. There's I've been interested in these things for a long time, and I've asked, for example, some of the world's leading graph theorists about how we can understand things about how localized structures might work in graphs. And I think a good example of a quote was, "Come back in 100 years and we may know more about how that works." Well, my hope is that one of the things that we're able to do now is, because we can actually simulate these things, and we actually have, we can build up our intuition from actually doing things with computers, we might be able to accelerate that 100 years a great deal. So one thing I might mention about particles is, one thing we would hope is that eventually we can derive from these underlying rules what particles should exist in the universe, and the fact that there are electrons and muons and tau leptons and gluons and photons and all those kinds of things. Let's talk a little bit about that, though. One of the issues is, just because you know the underlying rule doesn't mean that you immediately know its consequences. There's a phenomenon I call computational irreducibility that I started studying a lot in the 1980s, that basically says that the process of knowing what will happen, even in a system like this, can be can be something that requires an irreducible amount of computation. You might say, gosh, I don't need to, the rule is so simple, I can just jump ahead and say, this is what's going to happen a million steps in the future. Well, it turns out you can prove that you can't do that. Essentially, the reason is that whatever it is that you're going to use to jump ahead is itself like a computer, and this thing behaves like a computer, and those two things are essentially computers of equal power. There's a thing I call the principle of computational equivalence that says that, and that we have increasing evidence for, and that means that we just don't get to jump ahead. It's an irreducible process to know what will happen. And that's one of the things if we have this underlying rule for the universe, to know its consequences requires sort of an irreducible amount of computation. And among other things, to, for example, know its consequences for the, whatever it is, the 14 billion years that our universe has existed, we would have to essentially run the computation that corresponds to all those steps of evolution of our universe, which we don't get to do in the universe, and we don't get to really accelerate it much because of computational irreducibility. Now, The good news about computational irreducibility is that whenever there's computational irreducibility, there are always pockets of reducibility. There are always pockets of places where you can jump ahead. And those are the pockets that we have to kind of live in when we try and actually understand how the physics of our universe emerges from these underlying rules. Actually, I should say one of the sort of spectacular things that I really did not expect at all is that in these models that involve these hypergraphs and so on, it turns out that there's kind of a layer of reducibility that sits on top of this sort of underlying computational irreducibility. And that layer of reducibility is precisely what allows us to derive things like general relativity and will allow us to derive quantum mechanics. It's the fact that in these models, for reasons I did not expect, although it's sort of obvious after the fact, there are things about them that are both generic and don't depend on the precise details of the underlying rules and are not kind of ensnared by this kind of irreducible difficulty of computational irreducibility. So that's an important piece of why it's been possible to do this project so far. And we don't know exactly how far this computational reducibility is going to go. And we don't know, for example, whether it will allow us to derive things like features with local gauge invariance. I'm kind of expecting that it will. And we don't know whether it will go as far as telling us things like particle masses. My guess is it won't, and that those will be specific to particular rules. But anyway, so we can start to try and work these things out. I might just mention one thing. We know certain particles, they've been discovered by particle accelerators and all these kinds of things. We've got sort of a mystery in the universe that it seems like a large fraction of the matter in the universe is dark matter that we don't know what it is yet. So sort of the hunt has been on for what that might be. In our models, there are a bunch of, there's a sort of a question of what the spectrum of particles might be like. So one feature I'll talk about a little bit more later is it turns out that an electron, which is kind of the lightest non-zero mass particle, well, except for kind of the neutrinos, which have a weird way of having mass, that we know about. But in our models, for reasons I'll try to explain, there's reason to think that there might be particles incredibly much lighter than the electron, that are like 10 to the 20th times lighter than the electron, but not of zero mass. Non-zero mass, but very light compared to the electron. And that's sort of interesting because that's a potential candidate for things like dark matter. I've called these things oligons. The reason I call them that is because it comes from the Greek word oligos. It means few, and I call them that because they're things that involve, they're particles that involve few hyperedges in the spatial hypergraph. And so that's one of the things that's sort of a prediction of this model is the expectation. We don't know exactly where those particles will be, but that there will be particles very light compared to the electron that will exist. Okay. So somebody's asking what the sort of caption of this image. This is the Rule 110 cellular automaton. Okay, let's go on and talk about quantum mechanics. So let me see, what do I have here? Oh, okay. All right. So one thing, so quantum mechanics is this sort of strange feature of physics that was discovered originally around 1900, was the first inkling of it, and then it really sort of came of age in the 1920s. And my friend Dick Feynman always used to say, nobody really understands quantum mechanics. And I know I certainly didn't understand quantum mechanics before really recently. And there's still more to figure out about it. But one of the features of these models is quantum mechanics is not an add-on. It's not something where you say, oh, there's physics, we understand classical physics, we understand that there are certain laws of motion and things like that. Oh, now we have to add on quantum mechanics. That's another physics course which has to get added on, so to speak. That's not the way this works. It is absolutely inevitable in these models that one has to have quantum mechanics. And so the reason that comes about is the thing I was talking about earlier, that there are these rules, and there isn't just one way the rule can be applied. There are many ways the rule can be applied. And what we think about is apply the rules in all possible ways. And in a sense, all these different possible ways. So what a key feature of quantum mechanics is that it isn't the case that one always says a definite thing happens. In sort of classical physics, one says, the ball moves in this trajectory and it's definite. In quantum mechanics, one says the photon can go this way or it can go that way, and there can be interference between these different ways that it goes. And it's all something where one traditionally is just saying there's a certain probability of measuring it to be this or that. So there are these many paths of history that get followed, and we get to sample sort of the aggregate result of those different paths of history. And that's exactly what's kind of happening here. Now, so sort of this would be kind of the classical version is you just have those sequence of strings. I'm looking at strings rather than hypergraphs here because it's a bit easier to do that. Okay, so how does quantum mechanics then work? Well, these different possible things correspond to these correspond to the states that one talks about in quantum mechanics. Eigenstates, pure states, whatever, that one talks about in quantum mechanics. Okay, so here's sort of a big story of quantum mechanics. Turns out, in quantum mechanics, one should think about, one thinks about this is the sort of multi-way system of all the possible things that can happen in quantum mechanics. Now imagine that we're an observer, also embedded in this multi-way system, observing it. And we're trying to make sense of what's going on in all these different paths that are going on and the different paths going on inside us and so on. We're trying to make sense of all of this. What we'll end up doing is doing something very much like what we did in space-time. We'll make these kind of foliations. We'll say, we are going to view the world according to this particular reference frame. We're calling these things now quantum observation frames. There's kind of a new idea about how to think about quantum mechanics. This idea of thinking about it in terms of sort of reference frames, a bit like relativity. One of the things that happens in quantum mechanics is this idea that you make a measurement in quantum mechanics. There are all these different possible things that are happening, but at some point you say, I'm going to figure out, did the electron go that way or this way? You make a measurement, and then after you've made the measurement, it's definite. It's never going to change. That will be the result of that measurement. Now, one of the things that's been very mysterious in quantum mechanics is the fact that given that there are all these different paths of what can happen, how can it be the case that different observers, different measurements sort of are consistent? How can there be sort of an objective reality in quantum mechanics, even as what's coming out is just saying there are all these different paths and all these probabilities for paths and so on? And so this model of ours kind of explains that. And it turns out that the origin of kind of the objectivity in quantum mechanics, the fact that there's a definite reality in quantum mechanics, is precisely the same phenomenon of causal invariance. Even though there are different ways that one can make measurements, even though there are different kind of quantum observation frames that one can use, one still ends up with a consistent sort of view of reality. And that's a consequence, just like in relativity, the fact that we got sort of the same laws of physics independent of whether we were moving at different speeds, and that corresponded to different reference frames in relativity. So here, these different quantum observation frames correspond to different sort of slices of viewing reality, but nevertheless, because of causal invariance, they all ultimately correspond to the same reality. So what I'm showing here is kind of a cartoon version of a quantum measurement. What happens here is one's saying, okay, the quantum system is evolving, and then what happens here is the observer is deciding to make a foliation in which they're essentially freezing time. They're saying, I think this is the way things came out, and I'm sticking to that. And so I'm basically making these successive time steps all be scrunched together here. Now, again, a little bit complicated what's going on here. I will make an analogy. This is kind of what happens. So this is analogous to what happens in a coordinate singularity in general relativity, in space-time. It's actually analogous to what happens at the event horizon of a black hole. Effectively, what's happening is that you're freezing time. Now, in this case, you're just freezing time by a convention. The observer is choosing this way of setting up time. They're choosing to decide that time isn't going to change for them after they get to this state. And it turns out when they do that, things, in order to maintain consistency, they're sort of the region that is then frozen for them will get larger and larger. And that corresponds to quantum decoherence and to sort of the entanglement of states in quantum mechanics. Okay, so this is a super simple case. This is a slightly more complicated case. The real case is vastly, vastly more complicated than this. But this gives some idea of how you can have kind of time freezing foliations in this. Well, it turns out when people do quantum computing, they really want to freeze the state of a particular qubit. They want it to stay as a pure state. They say, this is the state, I want it to stay this way. And essentially what they are doing is to form a black hole in this multi-way space. So the thing to understand, and sort of a very beautiful analogy, I think, is that we talked about space-time. We talked about how there's a causal graph in space-time. We now are talking about the multi-way graph, and and we're talking about foliations of the multi-way graph, and those foliations are, as I was mentioning, directly analogous to the foliations that we do in space-time. And so one question that you can ask is, okay, we are, when we looked back at something like this was a foliation of a causal graph. The slices here, when we look at these slices and we say, what are the states associated with these slices? These slices correspond to instantaneous spatial states. So they correspond to spatial hypergraphs at a particular moment in time. That's what the foliation of the causal graph in space-time corresponds to, is spatial hypergraph. Okay, what is the foliation of a multi-way system? What does that correspond to? Okay, well, we can think of that, it turns out, as a thing we're calling branchial space. I'm sorry, my British accent probably ruins that word, but branchial. Unfortunately, Jonathan also has a British accent, and we're the ones who've been talking about this a lot, and so we don't really know if this works in American, but that's the word we're using. Okay, so the slices here correspond to what we call branchial space. If we kind of take that slice and look to the side, we'll discover that these successive steps correspond to the way that multi-way graph worked. They define connections between different states in branchial space. And those connections are a map, essentially, of quantum entanglements. This is essentially a map of entanglements in the space of quantum states. And so that's so this is then, we get to kind of analyze sort of the entanglements of quantum states. So again, there's space-time with this notion of extent in space. In the multi-way graph, the different nodes in the multi-way graph correspond to different quantum states, and there is a notion of a space of different quantum states, and there is this way that we can kind of knit together these different states by using not sort of positions in space, but instead entanglements in branchial space. And so what we've got is this notion of branchial space corresponding to the analog of physical space, but in the space of quantum states. Okay, so so now we can start asking questions. So we've got a whole setup. It's a bit like general relativity. Because we've got so a bit like relativity. We've got these foliations, and I would say that when we foliate the space, the thing what's going down the page here is still time, just like it was for space-time. But what's going across the page is not physical space, it's branchial space, the space of quantum states. And so then we can ask ourselves, well, is there an analog of general relativity in branchial space? And it turns out that there is. And essentially what's happening is, when we look at geodesics, the shortest paths in branchial space, those we can ask a question like, if we want to get from this quantum state to this other quantum state, what's the geodesic that goes from one quantum state to another quantum state? And we can ask about how those geodesics are affected by the presence of other quantum states. And so effectively what ends up happening is that the geodesics in branchial space have, when you want to get from one place in branchial space, one quantum state, which is a sort of position in branchial space, to another one, you're going along these geodesics, and the geodesics are deformed by the presence of other quantum states. And that deformation responding to each different path in the multi-way system. But basically, this multi-way causal graph is a representation of causal relationships, not only across through space, but also through branchial space. It's a representation of the causal relationships that between events that occur both at different places in space and at different places in the space of quantum states. Okay, and now it turns out that we can use the exact same definition of energy for the multi-way causal graph as we could for the ordinary causal graph. It's still a flux of causal edges. Now, in the details of the way that physics works, it's always been a bit mysterious how the energy of classical mechanics, in particular statistical mechanics, relates to the energy that appears in quantum mechanics. In this setup, the way it works is that they're both fluxes of causal edges. They're both fluxes of causal edges that, in a sense, decompose the same way, but one of them can be thought of as part of as flux of edges in the multi-way causal graph, the other in the ordinary causal graph. Okay, slightly complicated, but that means that when we are asking about geodesics in branchial space, just like in physical space, the geodesics, the shortest paths, are affected by the presence of energy, the same thing happens in branchial space. So in other words, the geodesic that determines the sort of the path that lets you get from one quantum state to another is affected by the presence of essentially energy in the system represented by a feature of the multi-way causal graph. Okay, so what? Well, the big so what is that the analog of Einstein's equations, effectively, which tells you about the deformation of this geodesics, tells you that the presence of energy that makes the geodesics turn. And okay, in slightly fancier physics, when you're talking about energy and momentum, there is a relativistically invariant quantity called the Lagrangian, which is sort of a combination of those things. And it turns out what actually matters here is the Lagrangian density. And that's what actually turns the geodesics in branchial space. Okay, well, the turning of geodesics in branchial space gives you the equations of motion of quantum mechanics. And so that, and the most direct way to think about that, my friend Dick Feynman, one of his great achievements was this thing called the path integral in quantum mechanics, which is the mathematical formalism that's sort of the underpinning of most modern ways to approach quantum mechanics. The path integral says you are looking at between one quantum state and another, the world can take many paths, but each path is weighted by a particular quantity, e to the is over h bar. And in this setup, we get exactly the path integral. In other words, when you look at these geodesics and the deformation of these geodesics, the way these geodesics are deformed is precisely the way they turn exactly corresponds to this e to the is thing. We're thinking about them as turning in branchial space. You can equivalently think about them in terms of complex numbers, but we're effectively thinking about them as vectors in branchial space. Branchial space is so that's a pretty big deal, that I think, that it's possible to derive the path integral from this underlying structure of the multi-way graph and the multi-way causal graph and so on. It's also just super cool that the fundamental fact of quantum mechanics is the same as the fundamental fact of space-time, and that essentially the analog of the Einstein equations is the path integral. So we might ask, what is branchial space actually like? Branchial space is very complicated. Whereas physical space is nice and tame and seems to be roughly three-dimensional, branchial space is much more complicated and sort of probably exponential dimensional. It's kind of like some kind of projective Hilbert space or something. It's a complicated thing, and we need to understand more about it. but we can already say things like these aggregate facts about geodesics and about the path integral without knowing more details about branch-Hill space. But to really understand branch-Hill space, we have to go and do more there. I should mention that the analogy between quantum mechanics and general relativity has another interesting piece. So, for instance, you might know the uncertainty principle in quantum mechanics, that if you make a for example, if you make a position measurement and then you make a momentum measurement, that the one measurement affects the other, or effectively that if you and that corresponds to the formalism of quantum mechanics, the non-commuting of the operators that represent the operation of doing a position measurement and doing a momentum measurement. So essentially, what one's saying is you do position, then you do momentum, and that isn't the same as doing momentum and then position. Okay, so turns out mathematically that is a statement that these operators do not commute. Okay, well, in general relativity, we have an analogous thing. We have so-called covariant derivatives. We have taking paths in space. So you can say, let's go horizontally, let's go vertically, let's go horizontally, let's go vertically. And when you're in a curved space, you don't get back to where you started from again. And that's a consequence of curvature. It's represented by the Riemann tensor in standard differential geometry and in studies of space-time. Well, it turns out that exact same phenomenon happens in branch-Hill space. You have the same, you don't get back to where you started from in branch-Hill space when you apply these two operators in two different orders, and that's exactly the uncertainty principle. Then there are all kinds of other things that you can derive in quantum mechanics, and Jonathan has written a nice paper that goes through some of the mathematical details of that. But anyway, that's the, okay. So let me now mention a couple of things here. And I'm getting closer to the end here. I'm going to talk a little bit about some of the sort of what this all means and so on. But let's talk about this sort of analogy between space-time and branch-Hill space, the space of quantum states. This is a very, very simplified representation of a multi-way causal graph in which we're essentially seeing kind of edges that correspond to edges that correspond to, this is sort of the time direction, and we're seeing there's extent in space and there's extent in branch-Hill space, okay? So we're now seeing sort of together, sort of physical space and branch-Hill space. Most of the time, physical space and branch-Hill space don't really get together much. Near black holes, they can get together, and all sorts of fun things happen. But let me mention another feature of this. So in space-time, one thing that happens is there's a maximum speed at which information can propagate, and that's the speed of light. And we can see that in these models, because in a causal graph, the maximum rate of information propagation here, let me pull up a causal graph here, the information propagates by going from one event to another. And we can make up light cones effectively by saying which events are in the future light cone, which events can be got to from this event here. And that you can only get to a certain cone of events in the future of that event. And the width of that cone essentially corresponds to the speed of light. And in a sense, the conversion from an elementary time going down here to an elementary distance in space going across, that conversion factor is precisely the speed of light. Okay, so in branch-Hill space, the same kind of thing happens. In the multi-way causal graph, you can make also cones that aren't light cones. They're now what we call entanglement cones. They're cones that represent the maximum speed at which you can entangle new quantum states. So they represent sort of a limit to the rate of kind of measuring more quantum degrees of freedom. Just as in the case of space, they represent the speed of light represents the maximum rate of kind of sampling new parts of space. So the maximum entanglement speed represents the maximum rate of sampling new parts of quantum space, new quantum states. Okay, so that maximum entanglement speed has some has, well, all kinds of consequences. Let me mention one thing that relates to black holes. So in a black hole, there's an event horizon, and the event horizon is associated with the fact that, well, you can think of it as a black hole is something where the escape velocity of the black hole is more than the speed of light. Nothing can get out of the event horizon around the black hole. That comes up that in our models, that event horizon is associated with a separation, a disconnection in the causal graph that corresponds to effects that can't propagate from one side of the event horizon to the other. So in addition to a physical event horizon associated with the space-time causal graph, in our models, there's also an entanglement event horizon that's associated. One can think of it as also exceeding the maximum entanglement speed, that effects would have to exceed the maximum entanglement speed. And so all sorts of bizarre things happen. So there's an entanglement horizon that actually sits outside of the causal event horizon. And the entanglement horizon is not localized in physical space, it's localized in branchial space, but it's something that's outside the space-time event horizon. And so that, if you follow the theory of black holes, there's been sort of an information paradox about black holes that has to do with where do the quantum degrees of freedom that sort of reside between a black hole that starts and a black hole that eventually evaporates in Hawking radiation. And I think we now kind of understand a way in which that works, which actually dovetails very nicely with a bunch of recent thinking about that's happened in particularly in the ADS-CFT correspondence and in the ER equals EPR work that's been done recently in theory of black holes and so on. But in any case, in our picture, what happens is there's this entanglement horizon that sort of sits outside of the causal event horizon, and there can be sort of quantum degrees of freedom that exist there and are preserved even when the black hole forms. Okay, let me mention one bizarre thing that happens. So in a black hole, I think in Russian, black holes are called frozen stars. And the reason for that is that if you look at a black hole from a great distance, it will never ultimately seem to form. So, and what will happen is, for example, if you're looking at a spacecraft that's falling into the black hole, falling through the event horizon, to you as an outside observer, it will seem to be freezing time right at that event horizon. It will never seem to go over the event horizon to a distant observer. And actually that freezing of time at the event horizon is exactly the same kind of thing as is happening here. When you try to make a qubit in a quantum computer, what you're effectively doing is to make a black hole in branchial space to try and freeze time around your qubit to prevent it from being affected by the rest of the universe. Same thing is, but now in the analysis of black holes, so in physical space, you're effectively freezing time as you go over the causal event horizon. What happens as you go over the entanglement event horizon? Well, if you're an observer there and something rather bizarre happens, effectively you are, I should mention another thing. When you go through the event horizon, when you go into a black hole, you get what's often technically called spaghettified. You get elongated, very sort of by the tidal forces of gravitation. You get kind of extended in space. Well, the same thing happens at the entanglement horizon. You get extended in branchial space. And one of the consequences of all of this is you basically can't do a quantum measurement there. It becomes infinitely difficult to do a definitive quantum measurement. So a way to think about this is at the entanglement horizon, an observer can no longer form a classical thought. They can no longer come up with a definite conclusion about what happened. They will always be stuck sort of having this quantum indeterminacy. And that means, for example, if they ask, when they have a couple of particles, like a pair of particles, and you say, did the particle fall into the black hole or not? The observer stuck at the entanglement horizon will say, I don't know. I can't form the definite classical thought of whether the particle fell into the black hole or didn't. So that's just one of the weird things that happens at the entanglement horizon. That's one of the places. So let me show you something. So one question is, I've talked about this structure of space and how it might be discrete and so on. So one question you might ask is, how big are these little connections in space? And I forgot to make a slide here, but so I have to show you. Actually, I might just mention in my more technical paper, there's kind of a table of what the different kinds of things that we know about in physics correspond to. So things like local gauge invariance, the expansion of the universe, conservation of energy, microscopic reversibility, all these kinds of things, virtual particles, all these kinds of things that one discusses in physics. We're trying to understand the analog of those in our models. By the way, I might mention one big analog is, in terms of cosmology, one of the mysteries of cosmology has been that when you try and mix quantum field theory with general relativity, there's sort of an incompatibility in cosmology, because quantum field theory says there's sort of an uncertainty principle about particles that says that in a quantum field, you don't know how many particles there really are there, and there's sort of this infinite soup of virtual particles that are getting produced. And those virtual particles will have an energy density that's absolutely huge. And that energy density would roll if you then applied that energy density in Einstein's equations, it would roll the universe up into a tiny ball. Well, in our models, that doesn't happen. And the reason that doesn't happen is because those virtual particles, all of that sort of bubbling around in the quantum field is precisely the thing that makes space in our models, because space is being made by the same kind of stuff that particles are made of. And in fact, so in a sense, space is making the particles. The particles are the space. And so you don't get to, that means it's not like the particles are added to the space and then curl it up. The particles are making the space. And so you don't have that same kind of issue with 0-point energy and so on. Anyway, let me go down and just show you something here. This is about, well, how big are these things? What is the elementary length? Okay, so one thing that people have often talked about is a thing called the Planck length, which is something you get from dimensional analysis in traditional physics. And the Planck length is very, there's a bug there. The Planck length is very, is something very involved in what we're talking about, but it isn't exactly what we're talking about. So we don't have a tremendously good way of estimating the elementary length, but we have a possible way of estimating the elementary length. And let me tell you how it comes out. So in the best estimate we have of the elementary length is that it's 10 to the minus 93 meters. Now that's really small. The Planck length is 10 to the minus 34 meters. And so this is really tiny compared to the Planck length. Actually 10 to the minus 35 meters times this quantity. So it's really tiny compared to the Planck length. And roughly the reason that's happening is it's the trade-off between the multi-way causal graph and the ordinary causal graph. And that the fact that what sort of matters is the multi-way causal graph is what's making things be much, much smaller than the Planck length. So that means the elementary time is at 10 to the minus 101 seconds in this estimate. And more importantly, the elementary energy is 10 to the minus 30 electron volts. In the case of the Planck energy, the elementary energy in the Planck sort of way of estimating things is actually 10 to the 19 GeV, which corresponds to sort of the energy of a lightning bolt. Doesn't seem like something very small in the universe. When you set this up in this model, the elementary energy is 10 to the minus 30 electron volts. So that means how many elementary lengths are there across the universe? About 10 to the 120. How many elements are there in the spatial hypergraph? About 10 to the 350. So these are big numbers. You know, how many updates has the universe done so far? 10 to the 119. How many individual updating events? If you date much bigger than that, it's possible that there's sort of a continuous doubling of a continuous sort of increase in the number of elements in space that even goes beyond this. But with these estimates, we can get things like the radius of an electron. So according to current physics, the electron is of zero radius. The intrinsic radius of an electron is zero. Quantum effects produce an effective radius, but the intrinsic radius of an electron is zero. Experimentally, we know that the radius of an electron must be smaller than 10 to the minus 22 meters. In this theory, in this particular estimate, we're saying that it's 10 to the minus 81 meters across, very small. That means, though, 10 to the minus 81 meters is actually quite big compared to the true elementary length of 10 to the minus 93 meters. And that means an electron is a big fluffy thing with like 10 to the 35 elements in it. And that's why when I talked about particles much lighter than the electron, that's why we suspect that those exist, because there will be stable structures in the network that are much smaller than something like this. Okay, so one of the consequences of all this is that we can estimate the maximum entanglement speed. And the maximum entanglement speed corresponds to about, we're calling it zeta. That's our analog of c, the speed of light, is zeta, the maximum speed in branchial space. And we can estimate that, and it's a bit big in this estimate. It's about 10 to the 5 solar masses per second. I might say that in branchial space, in a first approximation, whereas distances in physical space relative to times are measured by the speed of light, distances in branchial space are roughly measured by Planck's constant h bar. But when you deal with all this multi-way stuff and so on, you find out that what really matters is this maximum entanglement rate, zeta. And as I say, the maximum entanglement rate is in this estimate pretty big, about 10 to the 5 solar masses per second. So we, at our scale, don't usually encounter things that are like 10 to the 5 solar masses per second. But one can imagine that if, for example, there was a merger of black holes at the center of galaxies, that would correspond to those kinds of masses doing things in matters of a second. And then one would expect that this maximum entanglement speed would have a direct effect on what happens in that situation, and will produce different physical effects. And I might mention that there are other physical consequences of what we're talking about. So, for example, one that we were looking at just recently is what we can call frame dragging in photons that are in orbit around black holes. And that we would expect that as a result of the entanglement horizon, that correlations between such photons will be different from what you would expect otherwise. There are other kinds of predictions one can make. So another one that's really bizarre is one of the things with the universe is that on a very large scale, it has the cosmic microwave background gives us a sort of a map of what the very early universe, well, at least 100,000 years after the beginning of the universe, looked like in terms of where there was mass and where there wasn't mass. And presumably that mass eventually seeded the galaxies that we have in our current universe. The question is, what made those initial density perturbations? Well, 100,000 years after the beginning of the universe is an awful lot of updates in our spatial hypergraph. So we don't really know that we can deduce anything based on sort of early updates in the spatial hypergraph. But it's at least fun to think about the possibility that, for example, sort of breaking of symmetry associated with the very first few updates in the spatial hypergraph might actually have an effect on what we see in the cosmic microwave background. And I think it's more science fiction than fact, I think, because I don't think it's actually going to work this way. But we might imagine that density perturbation is essentially a shadow of the very first few updates in the spatial hypergraph at the very beginning, extremely large on the whole universe. I don't think it's really going to work that way, but something like that might be true. So we're back. Let me go back here. Where is it? We don't have a visual summary in the navigation. Okay, so I've given you a little bit of a tour of sort of how things work in this model of physics, from the underlying rule to all these different possible updates. The updates making the spatial hypergraph whose limit corresponds to space, the way that the different updates have certain causal relationships, and the way those causal relationships define space-time, and the way the different kind of foliations of space-time correspond to the reference frames of special relativity and so on. And then the way that this sort of multi-way graph of possible rewriting orders defines the possible the different possibilities in quantum mechanics, and then how this branchial graph of entanglements between quantum states arises, and how that lets one do the analog of relativity in sort of quantum, in the space of quantum states. So I wanted to just mention. So what else can we say? I think this is, I'm really surprised at how far we've been able to get. As I said, I thought, among other things, ultimately the underlying rule has lots of computational irreducibility associated with it. But there's this layer of reducibility that we've discovered that essentially gives us current physics. And one thing that should make that not so surprising is that we, as observers of the universe, succeed in making a coherent picture of what's happening in the universe. If we were immediately thrust into computational reducibility, that would be very hard to do. We wouldn't be able to really say much at all about what was going on in the universe. So in retrospect, it's not surprising that there's a layer of computational reducibility, which is essentially what we're keying into when we are sort of perceiving the universe and imagining and being able to make sense of what's going on in it. Okay, so I'm going to mention one more thing that is a little bit of a philosophically complicated thing, and which we've worked out less well than we've worked out the rest of what I've been talking about. And it's the following question. So let's imagine that we finally say, great, we've managed to find the rule for the universe. Okay? What, the question is, in a sense, why is it that rule and why not another? Right? What did we, isn't it weird that we got this rule and not another one? For example, if it's a simple rule, we're in a very strange scientific position, because if we look at the infinity of all possible rules, most of them won't be simple. So to say our universe got a simple rule is to say we're very special in our universe. Ever since Copernicus, basically, there's been kind of a view in science that we're not special. Our Earth isn't at the center of the universe, and so on. So how come our universe got to be one of the simple universes? How come it's that one and not another one? And I've been wondering about that for a long time. And the really strange thing is that I think we actually have a resolution of that question. And it's something that is, here's how it works. So I've talked about how each, at every step you can apply different, you can apply a particular rule to all these different, to make all these different possible updates. Same rule, but there are different ways that rule can be applied in the spatial hypergraph. Okay, so let's go really wild, and let's say we don't just have one rule, we have all possible rules. And we say, not only do we get to apply a particular rule in all possible ways, we also get to apply all possible rules. That gives us a sort of ultra multi-way system, a multi-way system where the branching is not just for different ways to apply a particular rule, but different rules we might apply, okay? So we've got this giant ultra multi-way system. So it turns out that it's basically inevitable that in that giant ultra multi-way system that we have causal invariance. And that means that there is a certain, that when we look at the consequences, when we look at certain kinds of consequences of this sort of rule of the set of all possible rules, that will actually end up finding out that we get definite answers for things that are guaranteed by causal invariance. And then what happens is that we can define foliations of this rule space, basically. And in fact, well, I should say causal invariance in rule space implies a certain rule space relativity. And we can define different foliations of rule space of this ruleal multi-way system. And what do those correspond to? We said that, for example, different foliations in space-time correspond in the space-time causal graph correspond to different states of motion. Different foliations in the multi-way graph, in the ordinary multi-way graph, correspond to different choices of quantum measurement sequences. Well, the foliations in ruleal space correspond to essentially different forms of description of the universe. It's getting quite abstract. Let me try and make a comment about this. So, when we say we are trying to find the theory for the universe, what do we actually mean? What we mean in the end is that we are trying to find a way to describe how a universe works in a manner that us humans can understand. If we just say, what does the universe do? Well, we can look at the universe and see what the universe does. But to say we want a theory for fundamental physics is to say we want something that we as humans can hold in our hands and sort of understand and find out that it does what the universe does. Now, it turns out that I don't think we humans get to do that. I think it's too far away from what our brains are set up to do. But we have a good intermediary, and the good intermediary is computers and computation. And I think what we're seeing when we are imagining a fundamental theory for physics is we're seeing this kind of three-way situation, where on the one hand, we've got humans trying to understand things. On another hand, we've got the universe just doing the physics that it does. And on the third hand, I suppose we're dealing with aliens here. We have kind of this computational, this medium of computation that's a way to sort of, that's a place where this process can occur. And so I've spent a lot of my life as a language designer, designing computational languages. To me, this is sort of a language design problem. Can we design a language that can bridge between these three things, humans, computation, and the universe? Can we design a language that will allow us to describe, to make a description across those three different things? And essentially what's happening when we look at foliations of Rullial space is we're looking at different possible languages. Each foliation corresponds to a different description language for the universe. And what this is effectively saying then is that in this kind of ultra multi-way system, we're saying that these different foliations correspond to different ways of describing the universe. Any particular foliation has a particular rule associated with it that will be the rule that we use that works with that description language. But another foliation will need a different rule with a different description language. That will be the one that it picks as its way to describe the universe. So one of the consequences this has is that, so we humans have a particular way we choose to describe things. We have a particular set of senses, we've developed a certain mathematics, et cetera, et cetera, et cetera. So we're kind of stuck in one particular foliation. It's not the only foliation. And we can imagine, I've often, I've talked about extraterrestrials and things like that, and I've often said, but at least they'll have the same physics that we do. But then I realized it isn't true, because they can effectively be operating in a different foliation. It's the same underlying sort of universe, but it's a different foliation, a different description language. And that different description language can be not just a little bit different, it can be utterly, bizarrely, incoherently different. So that the things that we identify as features of the physical world are just sort of thrown into dust in some other foliation, which will have a completely different kind of way of looking at the universe. So in the end, I think that the answer to why this rule and not another is, well, actually, it's all just on us. It's because we exist in this particular foliation. We explore this particular foliation of this kind of ultra multi-way system. And that's sort of the experience that we have of the universe. And that's when we say we're going to find the fundamental theory of them. Go back to, if I can figure this out. There we go. Okay. So that's the story, and that's kind of as far as we've got. A lot more technical detail. We're very happy to talk about. It's all accessible on the website. We've also made, as I mentioned, all the tools that we've been using for this investigation available. So if you go into, for example, my technical introduction, and you click on any picture there, you'll get the Wolfram language code. You can just run it in a notebook, and you should get the same picture that I got. Might take some pictures take a bunch of computer time, others do not. But we're hoping that this is sort of a foundation on which we can go and try and actually find the rule for the universe, so to speak. And we can try to understand how all of this connects to the things that are already understood in physics. I mean, I might say that pick some idea like string theory or like twistor theory or like causal dynamical triangulations or like topos theory or a bunch of other names of mathematical theories which have been developed in physics, I thought, gosh, these are not going to be relevant to the way that we're thinking about doing physics. But I was wrong. It seems that lots and lots of these theories are all talking about kind of limits and mathematical analogs of what we're doing. And I think that what we learn from those theories is going to be sort of super relevant to what's being done here. And I think that's one of the sort of early efforts, is to try and make all these connections between what we've figured out and what people have figured out with a variety of mathematical formalisms in these different kinds of theories. I might also say that from the point of view of mathematics, this is a very rich hunting ground, because we've basically, as is unfortunately very typical of physicists, we've kind of hacked our way through a lot of fine details of the mathematics to figure out how we can get to answers. And when you're dealing with limits where the parameter is 10 to the 500, there's a lot of hacking that's okay, because that's a very big number. But there's a lot of issues about what really is the multi-way causal graph. Is it really an analog of twistor space? Is it, what is the continuum limit of each of these things? What kind of mathematical structure is it? There are a lot of very interesting questions there. But anyway, so this is kind of introduction to what we're trying to do, and we're planning to live stream a bunch of the working sessions that we have about this. I would say that in the doing of this project, which we really started in earnest in about October, November of last year, so it's been a remarkably quick project. In the doing of this project, we started at some point when it looked like it was actually going to work. We said, gosh, we're having really interesting conversations, let's record them. So we actually have 430 hours of working sessions that we recorded, and we'll be putting those online soon. There's also about, how many was it? It's about 1,200 working notebooks that are sort of the scratch paper, so to speak, of this project, actually stretching back to 1994 when I really started working on this. And we just put all of those online today. And they should all be. The amazing thing is Wolfram language has been nice and compatible, so you can actually run the code even from 1994. So, questions that I don't know the answer to. So let's see. So I can turn over to questions here if people have them. So there's a question here that came a little while ago. What is the significance of Planck units in this model? I think I kind of answered that. The Planck units set the overall scale, but there's an additional quantity that we're calling capital Psi. It's my favorite obscure Greek letter that essentially represents the parallelism of multi-way space. And that gives results that are numerically very different. Numerically very different from Planck units. Okay, there's a question here. Do you think this methodology can help us study the emergence of life? You know, we're very far below things like living systems when we're studying the things that are length scales of order 10 to the minus 90 meters and so on. We're really deep down in the sort of the micro machine code of physics. So there's a pretty long way from that to living systems. Having said that, the mathematical structures that have emerged in this model of physics turn out to be, as is often the case, if you have a sufficiently simple model, it's going to be applicable to lots of things. And I actually think it is going to be applicable to a bunch of questions having nothing to do with its application in physics. Just the mathematical structures that we've built, I think, are going to wind up being applicable in a lot of other places. And I think one of the places is actually possibly to a theory of evolution. I think that Rullial space relativity thing that I was talking about might actually have quite a lot to do with that. When you look at these different possible rules, that's a bit like looking at the different possible genomes that can exist. And so there may be a essentially mathematical, not structural, but just mathematical analogy between what we're seeing in physics and what we're seeing as a sort of a global theory of evolution. That's one thing. I mean, even more bizarrely, we were looking as part of kind of helping with pandemic issues, we were looking at digital contact tracing, and we realized that the reconstruction of essentially, if you know just the whose phone interacted with whose phone, that kind of gives you elements in a causal graph. And the reconstruction of space-time, which is kind of who was where when, from the causal graph of whose phone interacted with whose phone, is bizarrely similar, again, to the mathematics of what happens in this theory of physics. So I think that we're going to see a bunch of applications of the structural theory here, in addition to applications to actual fundamental physics itself. And I might mention also that what we're doing here is essentially a big story of parallel computing. I mean, essentially what's happening is that in the operation of the universe, so to speak, we're saying there's a vastly parallel computation going on. In fact, one of the things that probably held me up from doing this project for a while was I just couldn't believe that the universe was such a profligate waster of computation as it seems it actually is, with all of these different paths being followed and so on. But that following of all those different paths is really a story that's like parallel computation. And in fact, this notion of causal invariance, these ideas of foliation and so on, these, I think, are potentially very applicable to approaches to parallel computation. And I think there will be a very interesting interplay between what one learns. I mean, the causal graph is a partially ordered set, and what one is essentially doing, it's like the universe is doing a breadth-first search and respecting this partial ordering of the partially ordered set. And you can think of it in a very computational way like that. I mean, in a rather bizarre sense, the universe is like evaluating an expression. And the whole operation, the whole history of the universe is the evaluation of an expression. If you think about it in terms of lambda expressions, there are the free variables of lambdas. And essentially everything in our universe is a bunch of escaped free variables from lambdas in this picture. Okay, let's keep going here. How long does this project spend? I'm not sure quite what that word means there. Will the work be published after peer reviewing? Well, yeah, I mean, we're just putting this out today, and it'll my giant 450-page document will I hope lots of people read it. I hope lots of peer reviewers read it, and then it will appear. Jonathan's papers, as I say, are much more suitable for equation-first readers, and they will go through that same process. But this is it's a fairly complicated conceptual structure that we built here, and it might take a little while to get well absorbed. Okay, what is a node and what is a line here? So, okay, so what we're thinking about is, tend to call them elements and relations. The nodes are just abstract elements. The only thing we know about them is that they exist and that they are distinct from each other. Those are the only things we know about them. We can call them 1, 2, 3. We can call them X, Y, Z. We can plot them as points in a picture. Do all kinds of things. But all we really know about them is that they are distinct things that exist. Okay? The lines are relations. They're saying these elements are somehow related. And a hyperedge, like a ternary hyperedge, would be a relation between 3 of those elements. And the way this model is set up in detail, the order of those elements matters in the relations. Probably doesn't need to work that way, but that's the way we're doing it. It's very general. So that's what it is. It's just elements and relations. Now we can represent the elements and relations. If the relations are just binary relations, that's what happens in a graph, where there are nodes in a graph, and the nodes in the graph are connected by edges, and there are a node at each end of the edge. That's like a binary relation. That's how we build up the graph. But as far as we're concerned, they're just elements and relations. They don't have that. That's what everything is made of, but it isn't really a thing that we can talk about beyond just saying it's these elements and relations. You have a path forward for replicating the laws of thermodynamics. Yeah, actually, I think I figured out the laws of thermodynamics in the 1990s. here's how it works. So the main thing that's mysterious, so the second law of thermodynamics is the big one to worry about. It's the law of entropy increase. It's the law that says typically what starts as very orderly, like motion of molecules, eventually turns into very disorderly motion of molecules that we call heat. You start off from some very structured, ordered thing. The molecules bounce around. The molecules eventually arrange themselves in a sort of way that seems completely random. So people had for a long time, so back in the 1870s, I think, Boltzmann proved this thing called the H theorem that says you can, based on looking at microscopic collisions of molecules, you can show that entropy increases. The problem with that was he also showed that entropy decreases because the way that we believe microscopic laws work is, for all practical purposes, for what matters for these, the laws are reversible in the sense that any collision that can happen forwards in time can also happen backwards in time. Small footnote to that, but it's not relevant for the derivation of thermodynamics. Okay, so there's microscopic reversibility, but macroscopically, once stuff is turned into heat, it never goes back from heat spontaneously. Once you've got that kind of randomness, you never spontaneously get order again. How can that work? Well, actually, it's and it was really quite unclear how that worked. I think in the end, let me see if I can pull up a something to show here. Hold on one second. If I can work this properly. What to do here? That's odd. I am not seeing what I would expect to see in my thing here. Well, maybe maybe I go there. Okay. All right. Show you something about this. This is my big book. There's a section on irreversibility and the second law of thermodynamics. And the main thing to understand is that you can have even a reversible system, and what happens is at some point it may have a simple be maybe in a simple state, but just as a result of kind of the computational irreducibility of the evolution, the thing will effectively encrypt that initial state into something that looks for all practical purposes random. So the origin of the second law is essentially that as observers with bounded computational capability, we see things going from lower entropy, more ordered states to higher entropy, disordered states. So essentially the second law of thermodynamics is a consequence of the computational boundedness of observers in the physical world. And that's how it works, I think. And for purposes in that way of setting things up, that's important in this theory of physics because it's what allows us to take these continuum limits to get ordinary space-time and things like that. But a quite separate thing is that I think that the origin of the second law is essentially computational irreducibility that is leading to essentially the encryption of initial conditions for purposes of computationally bounded observers. Let's see here. Okay, question about, can you talk more about the relationship between physical particles, virtual particles, and space itself? So I think what we're really, when we're talking about particles, let me show you another example, which I can also find in the NKS book, I think. Let's see where they are. Here's a good example. Yeah. So this is that Rule 110 cellular automaton that I was showing you. And this is just an analogy. In the case of spatial hypergraphs, it's more complicated, but here we get to sort of just lay the particles out. We already know how to lay the particles out in space-time. So here are some particles that are propagating around. And this is, these are particle collisions here. These are two particles colliding, making another particle. So a typical, we can sort of catalog the particles. Here's a bunch of particles that we can catalog. And when those particles propagate for an infinite time, that's like a real particle, like an electron in the language of particle physics and on its on the mass shell, the on-shell particle that has a in physics, p squared equals m squared, the form momentum squared equal the mass squared, something where the particle can propagate without making use of kind of quantum mechanics to exist. Now, in quantum field theory, there's this notion of virtual particles, particles that exist only for a short time, that sort of the uncertainty principle for particles makes that possible. And virtual particles rely on quantum mechanics to exist. And virtual particles are, in this, we don't know all the details of how that works in our models. But roughly, what's going to be happening is that those are particles that don't propagate forever in the spatial hypergraph. And not only that, they also are particles that have sort of an entanglement in the branch shell direction. And so they're virtual particles that exist as things that are not sort of completely defined in, they don't have an absolutely definite structure. They have a structure that sort of extends in branch shell space and can last only a certain amount of time in physical space and in space-time. And that's sort of the rough picture of how virtual particles work. But we have more to figure out there. In fact, one of the first live streams we'll probably do is probably talking about quantum spin and talking about that's sort of one of the pieces of what we need to understand how particles work. We'll talk about a thing called the spin statistics theorem. We don't yet know how to derive it. That's why we're going to try and figure it out. And that will be related to a bunch of these questions about how particles work. And so the question of the relation to space is these are just like, you can see this sort of background of pattern here. That's sort of the space in this very simple cellular automaton. And the particles are just following exactly the same rules as the background space, but they have this localized form. And it's the same kind of thing we think in the spatial hypergraph. But the background space is something more random. Essentially what these particles will be is a sort of topologically stable structure in this background space. So just like the little vortices in water that you can see that have a certain stability to them, not affected by even, for example, some turbulence in the water. So similarly here, there will be some kind of topological structure, although it isn't actually topology in the ordinary sense of topology, because we don't have certain data. We only have this connectivity data. We don't have more data about faces and things that you need to form ordinary topology, but it's something analogous to topology. Okay. Oh, I might mention another thing, which is you might ask the question, all these particles running around in space, how important is that to space? Well, I think that all of the real particles, that is, the virtual particles are a different story, but all the real particles in the universe might represent 1 part in 10 to the 120 of what's actually happening in the spatial hypergraph. So in other words, everything we know about particles, the vast majority, it's a tiny little piece of fluff on top of all of this activity, which is basically maintaining the structure of space. So, 10 to the 120, things maintaining the structure of space relative to one thing doing something with a particle. So that kind of gives you a sense. Most of the activity of the universe in this kind of setup and with this estimate of parameters is involved in the maintenance of space. And the existence of particles is just a small little twiddle on top of that. Okay, let's see. Everything in our universe, and that's what we get to have. And sort of the expansion of the universe is then associated with the expansion of this spatial hypergraph and so on. Okay, question from Justin here. What predictions have you made that you think would be easiest to verify empirically? So the first thing is, in a sense, theoretical verification. What do I mean by that? Well, there are emerging studies of things like black holes and so on that have made various inferences that are non-trivial inferences from existing physical theories. The fact that we can directly get to those inferences from this theory is significant. Now, anything to do with black holes is going to be somewhat theoretical. We know from gravitational wave detection that we know some features of black holes, but But by the time we're talking about sort of quantum effects around black holes, that's theoretical, but already there are theoretical predictions that can be verified in the context of the theories that have been being developed in the last few decades around those kinds of things. So that's first type of thing. The second type of thing is, being able to, is kind of things like these oligons, these very light particles. We don't know exactly what their mass will be, but the strong suggestion from these models is very light particles are very likely to exist. Similarly, some of these things about the early universe, similarly, this maximum entanglement speed, we just don't know the numerical value. Is it exactly 10 to the 5 solar masses per second, or is it 10 to the 4 solar masses per second, or 10 to the 6 solar masses per second? We don't know exactly. And to really know that for sure, we kind of have to find the actual rule, but we can already, there's a suggestion of things to look for, even though we can't nail down the actual parameter. As I mentioned, things like these correlations in photons orbiting black holes, things like that. My guess is there are also things to be looked at in quantum computing. This theory has definite implications for quantum computing. It has more theoretical implications than about what's in principle possible in quantum computing. Causal invariance implies certain limits on what's possible in quantum computing. And this maximum entanglement speed does also. But those things may be far away from what's experimentally accessible, or it may be possible to very cleverly arrange things in quantum computing so that you can actually see some of these effects like maximum entanglement speed. I'm not sure yet. I think that's going to be a bunch of hard work figuring out the details of what those predictions might look like. And once, if we can find a definite rule, then it's really going to be much easier to get very definite predictions, because we're going to know the exact scales for things and so on. I would say in terms of finding the rule, there are probably 5 attributes that we think the final rule has to have, among them, giving eventually 3-dimensional space, having certain properties about causal invariance and so on. We have rules, individual rules that have each of those probably 5 attributes, but we don't have a single rule that has all of those attributes. And it's a question of finding that. Actually, I think I mentioned before that we have this registry. Let me show you this. We have this, let's see, this registry. Am I sharing my screen? Yes, I am. We have this registry of notable universes, and you'll see here, let's see, this was some computed properties of this particular universe. The embarrassing thing is it could be that in our registry, we already have our physical universe with our description language, but we don't know that yet. But this is something we have to go explore. Okay, there's a question about the renormalization group in this framework. I think the renormalization group is alive and well in this framework. I think, how about we do that? If we want to talk more about the renormalization group, let's talk about it tomorrow in our Physicists and Mathematicians Q&A, because I think that's going to get fairly technical fairly quickly. Thoughts about Leonard Susskind's ideas around entanglement complexity. Let's see, is Jonathan online here? Maybe Jonathan would like to take that.
Yeah, I'm here. If you
go ahead.
Right.
Do you want to? You read these papers much more than I do.
Right. So it turns out that actually the geometry that's induced on branchial space, as Stephen was talking about it, seems to be remarkably similar to a lot of the geometrical ideas that Susskind has been talking about in the context of things like the ER equals EPR conjecture and stuff like that. And so one possibility is that, so effectively what happens is that different points in branchial space, their natural distance metric is expressible in terms of something like an entanglement entropy. And then things like the ER equals EPR conjecture, which is what Susskind is interested in, can then be formulated about in terms of correspondences between the multi-way evolution graph and the multi-way causal graph. But as Stephen said earlier, we should probably address this in more detail in the text.
We'll talk about it in full technical detail tomorrow.
Right. But the short answer is yes, it's definitely related.
Okay, next question is about string theory. And the question is this related to string theory? We don't know for sure yet. I was writing my sort of technical introduction to this stuff, and I wanted to talk about the analogy with string substitution systems. And I was thinking about the title of that section being, the case of strings, and I thought, oh my gosh, this is going to confuse every physicist because they'll think I'm talking about string theory. And then I started thinking, well, actually, is there an analogy between these string substitution systems and string theory? And it kind of starts as a pun that if you make these strings longer and longer and longer, and you're kind of looking at the continuum limit of an infinite number of symbols in the strings, what is that theory? And the absolutely bizarre thing is that pun may turn into physics. It may turn out that the continuum limit of string substitution systems is string theory, or more accurately, string field theory. We don't know that for sure yet, but that's an interesting possibility, and it's something that, well, I hope some string theorists will get into looking at that. And looking at how the analogy between what's happening in this theory and in string theory. My guess is that string theory will end up being sort of a simplified limit of some part of this theory. That would be my guess. Don't know that for sure yet. And possibly even this limit of these string substitution systems, which actually aren't the same as spatial hypergraphs. Spatial hypergraphs are, in a sense, much cleaner and have much less intrinsic structure than strings do. They don't yet have a notion of ordering and things like that in them. But that's at least my guess right now for how that might correspond. Can this model explain weak nuclear forces? So the answer is it's certainly better. The thing that we know that the weak nuclear force is associated with the SU2 cross U1 local gauge invariance that exists in the physical world. And there's a question here of, so local gauge invariance is kind of like, we can think of sort of rotation invariance as things are the same when you kind of rotate, the laws of physics are the same independent of which way you're rotated, so to speak. And there's a more local version of that, but sort of you can rotate locally and have it be the case that you can match things up in such a way that you still get the same laws of physics. There's an analogy of that in rotating in kind of an internal space that corresponds to the space of the so-called gauge groups. And actually, in our models, there is, I think, we very strongly suspect that local gauge invariance can arise rather easily in our models. And essentially the way it arises is that when you're doing updates, when you're applying these updates in different, you can apply these updates in different ways at a particular place in the spatial hypergraph. And there are multiple ways of applying these updates that essentially correspond to sort of a rotation in the spatial hypergraph. And that rotation in the spatial hypergraph is like the operations in the gauge group. And to a manifold, something like ordinary space, the guess is that the limiting of local rewrite rules around a particular point in the spatial hypergraph will end up corresponding, that the limit of those things will end up corresponding to a Lie group that will correspond to local gauge invariance in the system, and that will be what leads to the known local gauge invariance. And it's part of SU2 cross U1 is what gives you the W boson and Z boson and the weak nuclear forces. And I have to tell you, when I was a kid, the weak nuclear force was my favorite thing. And I even, when I was about 13 years old, I even wrote this book-length description of weak interactions that was all about that. So that was before gauge groups were really much of a thing. But I'm a super big enthusiast of the weak interaction in physics, and but actually we can already leverage what's been done in the standard model of particle physics to know that if we can get the standard model, we've got weak interactions. Let's see. Do all generative rules produce curvature-like objects in an emergent way? So the issue is, what is curvature and what is dimension? That's really a big part of the story. So we talked about measuring dimension by looking at the growth rate of these balls in the spatial hypergraph. Curvature is, and so dimension is kind of the leading term, is the exponent of the leading term in that growth rate. Curvature is a correction to that. So for example, it's r to the d times 1 minus r squared times the Ritchie scalar curvature over 6 plus d plus 6 times d plus 2 and so on. But in other words, the existence of curvature changes the rate of growth of the number of elements in these so-called geodesic balls. And so it's a complicated interplay between curvature and dimension. Once you say there's going to be finite dimension, then all the corrections to that, once you fix the dimension, the corrections correspond to curvature. Exactly what the interplay between curvature and dimension may be, there may be some slight surprises there in terms of sort of things that are mixtures of dimension and curvature, which we don't understand yet, because all the calculus we've ever built is in integer dimensional space. We don't really know what the analog of curvature is in fractional dimensional space. And that's what we have to be able to understand and to understand that interplay. Let's see, is there an equivalent graph with unordered edges to a given graph with ordered edges? Yes, there is. I talk about that in one section of my technical introduction. Actually, the stuff I was studying in the 1990s involved unordered graphs rather than these ordered hypergraph constructs. And the frustrating thing is that at the end of the day, after we do all of this work with all this very elegant system with elements and relations and so on, essentially you can get the exact same results with trivalent graphs. The only thing that's different is the enumeration of rules is different. So if you say, I want to find a simple rule that does this or that, the order in which you may enumerate those rules is a bit harder to get there, but I didn't, and so the sort of languished where that rule increases the size of the hypergraph. You can absolutely also have rules that decrease the size of the hypergraph, and yes, you can have a dynamic equilibrium between rules that are increasing size of hypergraph and decreasing the size of the hypergraph. I don't know whether that's going to end up being important. I'll tell you a kind of an allegory or something. When Einstein invented the Einstein equations for general relativity in 1915, one of the things that the most simple-minded equations he wrote down predicted is that the universe expands. And he said, but of course the universe isn't expanding. We can see that, we know that. So I'm going to add this thing called the cosmological term to fix that problem that the universe would be expanding according to his equations. And he later said the cosmological term was the biggest mistake of his life, so to speak, that because it turned out another 15 years later, it turned out, well, actually the universe is expanding. Now there's a lot of discussion about how big the cosmological term really is, and we now think there might be a cosmological term, long, complicated story related to virtual particles and zero-point energy and so on. But so in general relativity, Einstein made this mistake of saying, well, the natural thing is that space expands, the universe expands, but I'm going to put this hack in there to prevent it expanding. So I'm trying to avoid making the exact same mistake. It is certainly possible to have in these rules dynamic equilibrium where you have sort of a limited rate of expansion because there's also contraction, or you can have rules that just unboundedly expand. I don't know what's actually right, and we need to look at that. But I think to say, well, we obviously need rules that decrease the size is kind of making exactly Einstein's mistake, and I don't want to do that. So could this answer the mystery of dark energy and dark matter? So I mentioned dark matter. My best guess is that these things I'm calling oligons, these very light particles, much lighter than the electron, could be related to dark matter. The main issue with oligons is the question of how hot are they? How fast are they going? Are they going slow enough that they'll be caught in the gravity wells of galaxies and things, or not? That's a question of essentially, if oligons were produced in the very early universe, how do they get to the point where they interact only so weakly that they only feel the force of gravity, they don't feel any other forces, and as a result, as the universe expands, they effectively cool down. Now, particularly if they were produced at a time before the dimensionality of space ended up being 3 and before we had kind of the inflationary period in the evolution of the universe, I think there is good reason to think that they will be very, very cold, that they'll be very low energy, and that therefore they will be caught in the gravity wells of galaxies, which means that they are reasonable candidates for dark matter. Now, their interaction with anything other than gravity would be extremely weak, And so that's a challenge in terms of detecting them, and that's one of the questions is whether one can make specific models and try and do experiments around that. Dark energy is a little bit of a different story. That has to do with acceleration in the expansion of the universe, and that I think is more to do with if it exists and if acceleration really pans out in that way, is more a story of the exact structure of this of the way the spatial hypergraph works, and effectively in the derivation, like Jonathan has a nice derivation of Einstein's equations in which essentially the cosmological constant, which is what leads to dark energy and so on, arises as a constant of integration in certain equations. And so we can't determine from our most immediate derivation what that constant of integration is. When we have more knowledge about what the underlying rule is, we should be able to determine that. And that will tell us whether this sort of spatial hypergraph, whether the structure of the spatial hypergraph can add a dark energy term to the Einstein equations. So next question is, what does this tell us about the nature of time, and is there physics to it? Well, in these models, time is essentially associated with this sort of inexorable doing of computation. So the universe progresses through all of these different rules being applied, and it is the aggregate of the progression of the application of those rules that is the passage of time. And one thing to mention is that in ordinary physics, there are several different kinds of time. There's cosmological time, the time that defines the expansion of the universe. There's kind of thermodynamic time, the time that defines the increase of entropy and the formation of heat and so on. There's perhaps psychological time for us humans perceiving what's happening in the universe. In this model, one of the nice things is that all those kinds of time are aligned, and they have to be aligned because they're all associated with this underlying kind of computational process. Now, what happens is we know a lot about how time works in space-time and relativity and so on. What happens, as I was talking about before, is that in these models, all of that sort of structure emerges as a consequence of the sort of large-scale operation of the model. What you put into the model is time as computation. What comes out of the model is time in space-time, time as it operates in quantum mechanics, time in the ways that we're familiar with it in physics. But what time is in these models is computational. The passage of time is the operation of irreducible computation. And that's kind of a satisfying answer because it means that as time happens, something irreducible is going on. It's not like we can look at our universe and just say, oh, you don't need to run the universe. You don't need to exist for all these billions of years. We can just jump to the end and the answer is 42 or something. What this is saying is, in this model, we're explaining, no, actually, you can't do that. There's irreducible computation involved in the progression of the universe. That's what time is this irreducible progression of computation. And in a sense, that irreducible progression of computation really means something. It can't be done any way than to just actually run the universe and see what it does. We can't kind of jump ahead and immediately say, this is what the outcome is going to be. How confident are we that we'll find the rule? It's a good question. You know, last fall when we restarted doing this project, I didn't think we'd get anything like as far as we've got. I thought that we would be slammed into computational irreducibility almost immediately, that we would be looking at, you know, maybe we can get the first 10 to the minus 100 seconds in the evolution of the universe, but we'll not know whether it really connects to the universe as it exists today. It's worked a lot better than I expected because there's this layer of computational reusability that we've discovered in these models. Now, searching for the rule that corresponds to our description language and so on, I don't know how hard that's going to be. I really don't know. And I don't know whether, you know, I was going to, I don't know whether we're going to find it this month, this year, this century. It is not easy to predict that because we just don't know whether, essentially what the question is, how good a description language is what I've been telling you today? How close is this to aligning between us humans, the physical universe, and computation as we know it. How successful have we been at aligning those things? If we're successful enough, the rule is going to turn out to be something very simple expressed in that language. And we just don't know how successful we are at doing that. And so we just can't tell how hard it's going to be to find the rule. I mean, we're going to be doing all kinds of searches for it. Hopefully other people will as well. It's not trivial to set up criteria. One of the things that happens in searching the sort of computational universe of possible rules, my little mantra is the computational animals are always smarter than you are. Anytime you set a trap for them, anytime you say, I'm going to use this criterion to decide which ones are interesting, you'll find ones that somehow manage to squiggle around that trap. They do things that you absolutely didn't expect. And so it's a little bit difficult doing these systematic searches, but you know, we'll do a bunch of these, and hopefully other people will help in doing that, and that will help in homing things down, and then we'll have to do a bunch of thinking about it. Let's see, can we talk about emergent effective differential geometry from fundamental computational rules? Absolutely, absolutely. The differential geometry that emerges from that's exactly what we're doing. We're saying when there is a finite dimensional space that emerges, it has certain properties that have certain differential geometric features that happen to correspond to Einstein's equations. When you happen to end up with something whose limit is integer dimensional space, you can go to town with traditional differential geometry. You can define Riemann tensors. You can talk about Christoffel symbols. You can look at you know, equations of geodesic deviation. All these things. They all just work. They are more elaborate and less well defined in fractional dimensional spaces. That's kind of a math thing that still needs to be figured out. Let's see, a standard sci-fi question. Can you go faster than light? Is time travel possible? Okay. The can you go faster than light? Complicated, because in branchial space, you're reaching, that's a slightly complicated thing. You can have entanglement like you do in quantum mechanics, but the light cone is, and depending on how wild the structure of space-time is, you can have wild wormholes and things like this, but they'll work in pretty much the same way as they do in general relativity, I think. That's the story on faster than light travel is it's kind of going to be the same as general relativity. A story on time travel, closed time-like curves, is yeah, you can have rules that give closed time-like curves in the multi-way graph, for example, but those rules do not admit the possibility of foliations that are kind of consistent time foliations. So again, closed time-like curves end up being like a consistency condition between different parts of the system, and they have sort of trouble in terms of, well, they have trouble for causal invariance. They have, essentially causal invariance says you can't have closed time-like curves. So you don't get, but time travel is a messy concept anyway. The basic answer is you can't have it in these kinds of models. Antimatter problem. So one question about the universe is there's matter and there's antimatter. By the way, we don't yet know in our model how antimatter works. To every particle, you can apply to every particle this operation of charge conjugation that goes from a particle like an electron to its antiparticle, a positron. And there's a question of how that will work in these models. We don't know that for sure. The first thing we expect we would get is a thing called the CPT theorem, which says that if you do charge conjugation, parity, that's space inversion, and time reversal, that the result of all those three things is guaranteed to, in traditional physics, Lorentz invariance, relativistic invariance, guarantees that CPT invariance is an invariance of any theory. We haven't shown that yet in our theory, but I don't expect it to be that difficult to show that. And that will at least give us some hint about how antiparticles work and how one gets, actually, as I think about it, I have an idea for how that might work, which I hadn't thought about yet. See, we've been in the last few weeks, as we've been sort of preparing this for to be able to present things on the website and so on, we've had kind of a no science policy, because we know that if we start doing more science, it will be a never-ending process to get to the end. It actually reminds me of Zeno's paradox, and I have to mention something I forgot to mention when I was talking about it. I mentioned time dilation in relativity, relativistic time dilation. It turns out there's a similar phenomenon in quantum mechanics. It's called the quantum Zeno effect, that basically says if you measure too often, you won't see things changing. So essentially, time is dilated if you make too many measurements. And in our theory, that's very beautifully comes out. It basically says as you move in branchial space, that motion in branchial space gives you a time dilation, and that is the quantum Zeno effect. But anyway, we were worried about a Zeno effect for this project, where if we do too much science, if we just keep doing the science, we'll never end the project, so to speak. So anyway, one of the things we should talk about is charge conjugation, and I just had an idea for how that might work. So, and I think but about antimatter in general, one of the mysteries of the universe is that there doesn't seem to be much antimatter in the current universe. It seems like and we might have thought that in the early universe it would be symmetrical between matter and antimatter. Actually, I worked on that problem back in 1980, trying to figure out why there's more matter than antimatter in the universe, and came up with a definite theory about that, which we don't yet know whether it's right or wrong, because it involves some particles much heavier than things we've been able to see so far. The core phenomenon that leads to the possibility of matter compared to antimatter is violation of CP invariance. So the universe seems to be invariant with respect to rotations, for example. But if you do a space inversion, if you just negate all the coordinates, so-called parity transformation, the universe is not invariant under that. The weak interactions, for example, well, actually the most obvious thing is neutrinos are every neutrino is almost exactly left-handed, in the sense that its direction of motion and its spin is always arranged in a kind of left-handed way with respect to its direction of motion. And that means that space inversion, the universe is not symmetric under space inversion. The universe is also, so I mentioned the universe is invariant under the combination of charge conjugation, parity, that's space inversion, and time reversal. It seems to be invariant under that. But individually, it's not invariant under any of those. And it's also not invariant under CP, charge conjugation, and parity, or equivalently under time reversal. That inequivalence is, at least in the theory that I talked about around 1980, that is what leads to an excess of matter over antimatter when you combine it with the expansion of the universe. But we don't know how that's going to work in our models. And for example, there's a small amount of CP violation that is observed in particle physics. Being able to reproduce that in our models will be really cool. Don't yet know for sure how to do that. We may or may not have to actually start constructing things that represent particles like quarks and so on to be able to get that, or it may be something more generic. I kind of have a slight suspicion it might be more generic, which makes it possible to kind of figure it out without knowing the ultimate rule. Let's see. Is the model consistent with the Everettian multi-worlds theory? How about we send that one to Jonathan here? Jonathan, do you want to take that?
Yeah, sure. Okay. So the answer is it essentially is. So this whole notion of multi-way evolution, the way we've constructed it and its connection that we conjecture it has with quantum mechanics, is very reminiscent of the many worlds interpretation of quantum mechanics. So the simplest version of the Everettian interpretation, where you have non-interacting branches of quantum evolution, that effectively corresponds to the special case in which you have just a multi-way evolution graph where everything is branching and you get no convergence between states. In the more sophisticated kind of Deutschian version of the interpretation, where you get interaction between parallel branches of evolution history, that corresponds to our notion of kind of multi-way merging, and this notion that Stephen was talking about earlier of walling off states within sort of event horizons of quantum observation frames and things. There's more detail we can give, but we should probably save that for tomorrow.
Okay, question from David here. Are we saying that the universe is deterministic? The answer to that is simple. The answer is yes. However, it's a little bit more nuanced because we're saying that there is this multi-way graph that has all of these different evolution histories, but we as observers of that graph are basically slicing across different ones of these histories. But the ultimate complete multi-way graph is absolutely deterministic. Our perception of it may not seem deterministic, but the actual progress of all those possible branches is completely deterministic. If you ask questions like, okay, what does that mean for free will? Well, that's all about computational irreducibility. Computational irreducibility is what gives us an impression of free will, because even though everything is determined, you can't know what's going to happen effectively more efficiently than just running it by running the computation. So you can't know, oh, it's not like, you know, the 1950s style robot science fiction thing where like the thing operates according to logical rules and therefore you can predict what it's going to do. It doesn't work that way. Because of computational irreducibility, one is sort of stuck having to just follow the progress of time to know what's going to happen. How do you measure if the rules one has are successful? That's a good question, and that depends on this whole computational irreducibility versus computational reducibility question. In other words, the ultimate question is, do we reproduce the parameters we know in the universe? Do we reproduce that there are 3 dimensions of space? Do we reproduce that the muon electron mass ratio is 206? Do we reproduce that neutrinos are primarily left-handed? All those kinds of things. That's what will ultimately determine whether we found the rule. But we can already say, so here's one thing. If the rule is simple, then as soon as we get 3 dimensions of space and, you know, electrons and muons and tau leptons and things, I would be amazed if it wasn't actually the rule, because the distance between one simple rule and the neighboring simple rule will be huge with respect to its effect on the universe. So going from one rule to the sort of nearest neighbor rule, you'll go from 3-dimensional space to, you know, infinite exponential space to something, you know, wildly different. So as soon as you've got the basic parameters of the universe, you can be really, I think, very confident that everything else is going to fall into place. But so that's the best hope, and how difficult it will be and which parameters we will find first, I don't know. For example, I have a suspicion that the local gauge group is going to be a direct window into the underlying rule, that's going to constrain the underlying rule a lot. In a way, at length scales of like 10 to the minus 93 meters. That's incredibly far away from what we have right now. You know, if you've got a pet black hole in your backyard, then there's a lot more you can do, but we don't have any pet black holes, probably for the better. The question of whether by doing some kind of quantum measurement process and by doing some iterated quantum measurement process, you could have some strange effect through this whole branchial space thing. It's conceivable. It's conceivable there might be some way to sort of teleport through space in some elaborate way by making use of some feature of branchial space. I don't know. Right now it seems far away, but I'm not sure. I mean, it's worth remembering that in particle physics, we still don't have a single sort of practical application of anything beyond the ordinary particles. There's no strange particles, for example, or charm particles, whatever. There's nothing yet that's been sort of reduced to practice. Even relativity, that's 100 years old, we're still only at the very beginning of having things where relativity really matters. In practical, in directly matters in sort of practical things we measure, use in engineering and so on. Okay, question about oligons and neutrinos. How much lighter than neutrinos will they be? Well, we don't know. We know the neutrino mass matrix. We don't know the individual rest mass of neutrinos, but we know that neutrinos mixing with other neutrinos have certain rates. I'm trying to remember the bounds on the neutrino masses right now. I'm the point is that we're still isn't quantization of space-time, energy, momentum, and mass. In these models, those things are quantized, but the individual quantum units are really tiny. And the point is that I'm sort of guessing that you can have particles that are a small number of quantum units of mass, and those are really, really tiny, 20 or 30 orders of magnitude smaller than current bounds on neutrino masses. But that doesn't mean that there couldn't be a whole spectrum of particles that live in that space, so much lighter than neutrinos, so much lighter than all these other kinds of things. I mean, neutrinos have very weak interactions. That's part of why they have low masses, but there may be other reasons. It's kind of complicated. It's not directly connected to that. But you know, this possibility, which really had never occurred to me, at least, that there might be, you know, 20 orders of magnitude or 30 orders of magnitude of lighter particles, I've never really considered, and I think that's an interesting kind of thing, even when we don't know the full parameters, to start considering. Okay, good question. Next one. How is the graph stored? 10 to the 500 steps requires a fair amount of memory. Yeah, it requires all the memory in the universe. It is the universe. I mean, this is one of the kind of philosophical questions that comes up when you start saying the universe operates according to a rule. It's a kind of computational rule. People start saying, well, what's that rule running on? You know, where's the computer that's running this rule? Well, it doesn't work that way. The rule is just a description of how the universe works. It's like when we know that the motion of planets is governed by differential equations, we don't think that the planets have little mathematicas inside them solving those differential equations. We're merely saying the differential equations are a way of describing how the planets move. And it's the exact same thing here. We're saying these rules are a way of describing what the universe does. The universe is equivalent to performing these computations. It's not that the universe somehow is externally performing these computations. It's just the actual stuff the universe is the performance of these computations. And so that means the data structure of the universe is the universe. The computer of the universe is the universe itself. It's running itself, so to speak. And by the way, I mean, it's interesting to kind of see all these things about computation, all these ideas about computation, like trade-offs between space and time and computation. That's actually physics. The trade-off between space and time is related to relativity and light cones and things like this. The question of, I mean, by turning what one has done in a theory like this is one's conflated three things. One's conflated computation, physics, and mathematics. They're really ultimately all the same kind of thing. So, you know, mathematics is something where you start off with sort of axioms and then you say, well, what are the deductions you can make from that? Physics has always been this empirical theory where you say, well, the world roughly works like this and this is an approximation. But this is saying that we can actually find the rule, the precise thing, like an axiom in mathematics, where just by working out the consequence of that rule, just like we work out the axioms in mathematics, we know precisely what the universe does. Of course, there's computational irreducibility, so it's irreducibly hard to actually do it. But from a conceptual point of view, this will reduce physics to mathematics. And similarly, in a sense, it's reducing physics to computation, and it's providing kind of and we can actually think about computation then. The universe is just an example of a parallel computation, and the laws of physics will also be laws that apply to these parallel computations. And so we can start talking about sort of relativistic things. And I haven't figured out yet, this is another good thing we should talk about, is the analog of time dilation for space-time trade-offs in parallel computing. But I think all of that formalism will be able to be interconverted there. Are there any implications of this in the near term for an average person? My theory is there are no average people, but anyway, here's the way I think about that. Is there going to be technology that operates on the basis of elementary lengths of 10 to the minus 93 meters? Not anytime soon. I think the main significance of this is probably a conceptual one. I mean, I would say that you can sort of draw a slight analogy to, like what Copernicus did in back in 1500 or so. People had always thought, the sun goes around the earth, all those kinds of things. There was this whole theory of, Ptolemy's theory of epicycles, all those kinds of things work just fine for predicting the motion of planets. Even today, when we, work out when an eclipse is going to happen, we're basically using the computational analog of tens of thousands of epicycles. But what Copernicus did was he showed that actually there was a mathematical theory that you could set up that didn't follow what we sort of perceive from our senses, that the earth is stationary and the sun is moving around it, but that actually said, well, no, that's not really the case. This mathematical theory shows that you can have the sun at rest and the earth moving around it. But the theory was kind of complicated and it had a lot of technical detail. And, I don't know how many people cared about the theory, but the consequence of the theory was that the science and math can tell you things that weren't obvious from everyday from your ordinary senses. And that started a huge progression of kind of scientific thinking that said, just work out the science. Don't, the fact that you can't figure it out by pure thought, by just pure reasoning, isn't really the important thing. Science can figure it out. But I think what we're seeing here is that we're sort of seeing a foundation for physics, for our understanding of the physical world, that's rooted in computation. And once we really believe in the fact that computation is what it's all about, once we really believe it's all computation kind of all the way down, that has consequences. And so, for example, one of its important consequences is the phenomenon of computational irreducibility. You simply can't get out of computational irreducibility. Once things are computational, you will have computational irreducibility. And computational irreducibility has everyday consequences. It's the thing that tells you you can't just figure out what's going to happen by just sort of pure thought. It's the thing that tells you can't know whether a program is going to have a bug in it without running it. It's the thing that tells you when you have an algorithm for deciding what content should be in a news feed and some AI-based algorithm for that, you can't know what its consequences will be without effectively running it. It's the thing that kind of limits the effectiveness of science to make sort of global predictions. It's a way that science, it's sort of interesting that for example, in the Copernican case, that was kind of just trust the science, it's going to figure everything out. What we're saying is when things are rooted in computation, there are inevitable limitations of science that come about just by the nature, just by the logical structure of the way that science is built from computation. And those center around computational irreducibility, and those imply certain limits on the way that we think about science. And so I think from a sort of everyday point of view, the thing I would say is it's sort of a different way of understanding the world. And, from the time of Newton and Galileo and people like that, we got concepts like momentum and force and so on. And those concepts originally were concepts in physics, but we've been able to sort of apply them to our general thinking about a lot of kinds of things in the world. We talk about, the momentum of some product, which isn't the physical motion of the product, presumably. It's something more conceptual. And we think about those things in a conceptual way. And I think knowing that things are rooted in computation gives us a way to think conceptually about the world with concepts like computational irreducibility, principle of computational equivalence, undecidability, those kinds of things that I think will have a general applicability to our way of thinking about the world, far beyond the specifics of the details of how the physical universe happens to work. The next question was, is the universe a simulation? I think we can fairly say that question really doesn't make any sense. And let's see, Jonathan and I just worked on, this is one of these questions which always takes me a little while to unpeel philosophically. And Jonathan and I just worked on a nice succinct answer to that. Let me see if I can find that here. It's in the Q&A section on the website, and I think we might have a, okay, here we go. So actually, I guess I wrote this. Jonathan was somehow involved in this. So, I mean, the first point is, if there is a definite rule for the universe, it means everything about the universe is determined from that rule. There are no external miracles in the universe. There's just this rule that determines how the universe works. And so then to say that the universe is a simulation would be to say there is something intentional about this rule. There's something set up this rule to be the way it is. Okay, so there's a notion of some programmer programmed this rule on purpose to be this way. Okay, well, we already get into trouble trying to go take intentionality outside the domain of humans. Maybe even to animals we have trouble. But by the time we're dealing with AIs, we have a lot of trouble. And by the time we're dealing with other systems in nature, like, we might say the weather has a mind of its own. What's the weather trying to do today? Is the weather trying to make us wet? What is it trying to do? Is there a way of transferring our notion of intentionality to these other kinds of things? That's already very hard to do. So in this case, what we'd be doing is transferring intentionality to the whole universe and saying, in a sense, was something outside the universe intentionally putting in this rule? Okay, that's the first problem. The second problem, that in a sense is an even worse problem, is that in a sense, this rule-space relativity idea implies that all possible rules for the universe are in some sense equivalent. The rule that is the one that we are identifying in our sort of foliation of the universe is the one that corresponds to our particular way of understanding the universe, our particular description language for the universe. And so it doesn't really make any sense to say, somebody can decide on a rule, but any possible rule would work. The rule that we kind of consider is the one that is operating, is the one that fits into the description language that we can create. So it's not something you can really insert from the outside. So I think we're really pretty unraveled in terms of being able to say the universe is a simulation. I think that really isn't a sensible thing to say, I think. I'll add one weird footnote to that. The one thing that in the end one could say about the universe, after you cut out all these different possible rules, all these different possible description languages, the one thing that shines through is the universe is a universal computer and nothing but a universal computer. So people have wondered, is the universe capable, when we have all the computers that we can construct, so far as we know, are all ultimately equivalent. We can program one computer to behave like any other computer. We can make a Turing machine be able to model any kind of, be able to emulate any kind of computer that we construct, whether it's the computer in our CPU chip or whether it's the computer that corresponds to some physical process. All of these things can be emulated. Well, we know we can do it for the things that we normally think of as computations. But the question, what this model is implying is, the one absolutely certain thing we can say about the universe is the universe is just a universal computer and nothing but. And for example, can you say, well, what could be more than a universal computer? Well, here's an example. A Turing machine, for example, it might just go along and it might go along, and you might say, is the Turing machine ever going to halt? Ever, even after an infinite time? Well, to know that, it's a computationally irreducible thing. So you might have to go an infinite time to find that out. But you can imagine building a sort of super Turing machine, a hypercomputer, that would just immediately be able to answer the question. It would just say, yeah, this Turing machine you've got, after an infinite time, it will halt, or it will never halt even after an infinite time. And so a hypercomputer is something you can imagine, but the question is, can we build a hypercomputer in our physical universe? And this model says, no, you can't build a hypercomputer in our physical universe. And in fact, this kind of rule-space relativity thing implies that even if there was a hypercomputer that was sort of, that our universe, even if there were rules for our universe that were possible, that corresponded to hypercomputing, there would be essentially a cosmological event horizon that will prevent us ever communicating with those rules that correspond to hypercomputation. So there really isn't a lot of room for a programmer in this whole story. Okay, let's see. So this question about an approximation to how large the bits in the underlying rule are, we have a way of estimating that. I think it's a little bit flaky, but the estimate we have is 10 to the minus 93 meters, which is really small. Let's see. Okay, if we calculate a very fine grain, we should be able to converge to something which seems continuous. Is that continuous like continuous space? This doesn't really give us any more of a way to do continuous computation than we're still doing the computation in the universe, so we still have to construct the computational elements out of things in the universe. This, I think, might give us some interesting ideas about how we could do sort of massively parallel computation, but I think that's a different kind of story. Question about why there are 4 fundamentals. The other 3 forces, we can see how those might arise. Those forces are all related to quantum mechanics. But the real test of those forces, they're known to be associated with local gauge invariance. And if we can reproduce local gauge invariance, we will reproduce the possibility of those forces. But we haven't done that yet. We have an idea of how that might work. Okay, suppose you had the rule to make useful descriptions of large-scale phenomena, would you need to run the simulation because of computational irreducibility? Ultimately, yes. To find out that I'm doing this live stream right now from the underlying rule for the universe and the initial condition for the universe, we have to run that rule for whatever it is, 10 to the 500 steps to get to this point. And unfortunately, computational irreducibility means we probably have to really run basically those 10 to the 500 steps. And that's something that we don't get to do in our universe. Our universe just did it, but we don't get to do it in our universe. Now, the hope is that there are pockets of computational reducibility that will allow us to make general statements without having to run all of that irreducible computation. And one of the big surprises in this project is how thick the layer of computational reducibility is that allows us to derive Einstein's equations, derive the Schrödinger equation, derive the path integral, all these kinds of things that don't seem to get enmeshed with computational irreducibility. Their detailed parameters, detailed features of particles may very well get enmeshed in those, but these general features of physics do not get enmeshed in those things, and so we're able to derive them. And so that's kind of the how far the boundary of reducibility is, we don't know. I mean, the realization sort of after the fact is we kind of know there's somewhat thick layer of reducibility because that's why we humans can make any sense of the world. If everything in the world was immediately thrust into computational irreducibility, we wouldn't be able to make any sort of general statements about how the world works. We wouldn't think that there was sort of that the universe worked in a coherent way. It would be all thrust into this sort of very low-level computational irreducibility. Let's see, how does the observer effect fit into this theory? Well, I mean, a lot of what we're talking about is the interplay between the observer as part of the system and the system itself. The fact that when we try to analyze the system, we're analyzing it in terms of causal graphs that represent causal relationships between events. And we're analyzing it in terms of these foliations of the causal graph and so on. That's all about trying to effectively model the way that an observer who is embedded within the system interacts with the system. You may be meaning by observer effect, you may be meaning things like the uncertainty principle. I talked about that a little bit earlier, about well, again, it's all related to the observer as something embedded within the system, but that's also related to the geometry of branch yield space and some other kinds of things. But I'm not completely sure what's meant by that. Hey, Jonathan, do you have a better thought about that?
Well, yeah, okay. I may be able to add something. So when people talk about the observer effect in quantum mechanics, as you say, they're normally meaning sort of the effect that the observer can have on the outcomes of certain classes of quantum measurements. And effectively in our model, this comes down to the thing Stephen was talking about earlier about these QOFs, these quantum observation frames, where, so in the same way as in relativity, if you have different relativistic observers, they can see different orderings of space-like separated updating events. In the quantum mechanics case, where you're in the multi-way evolution graph, different quantum observers, depending on the identity of the quantum observer, you can see different branch-like orderings of measurement events, effectively, is how that works. And again, this is probably something we can address in more detail later.
Oh, good answer.
Thanks.
Okay. Let's see. Does the amount of computation in the universe increase over time as it grows in richness and complexity? Is it possible to quantify how much that is? What is the clock speed of the universe? Okay. So the answer to that is yes. The amount of computation that's happening, in a sense, does increase in time because, well, at least time as we perceive it, because the way that we are foliating time, the way that we are deciding what counts as the next moment of time, we're imagining that moments in time sort of go across the whole universe. So assuming that we use the sort of the way of measuring time that is the typical way that we think of measuring time, then the answer is that the spatial hypergraph is increasing in size as the universe evolves further. And we kind of, and it's basically certain. The spatial hypergraph is increasing in size, probably related to the expansion of the universe. And that means that, in a sense, for every new time step in this kind of foliation of time, more pieces, more underlying nodes in the hypergraph, more underlying relations have to be updated to get to the next thing that we consider the next moment in time. So in that sense, yes, the amount of computation is increasing as we go through the evolution of the universe. What is the clock speed? We actually have an estimate of that. Let me just look up because I'm forgetting, which I shouldn't be doing, but let me just see here. Let me see. I should know all this immediately, but I also don't think these estimates are yet that solid. Let's see. Okay. Yeah, so the estimate for the elementary time is 10 to the minus 101 seconds. So that would be the clock speed of the universe. That is the time elapsed between two updating events on a single causal edge. Between two updating events will be 10 to the minus 101 seconds in this estimate. And that would be, in a sense, the clock speed. This question, so there is an interesting feature in rule space. There is also the notion of a maximum speed in rulal space, and that maximum speed is related, and we don't understand that well yet, is related to essentially a maximum speed of translation between different description languages. So I think what that's going to do is it's going to link algorithmic information theory, which talks about the complexity of program sizes, with features of physics. And I think just like we have the speed of light as one fundamental constant of the universe, I think we have another fundamental constant, which is the maximum entanglement speed that I'm calling zeta. I think there is another fundamental constant of nature, which is the maximum speed in rule space, which we're calling rho. And that maximum speed in rule space is essentially the maximum rate at which translations between description languages can occur. And that, as I say, is somehow related to gives a scale for program size, which is, so just as the speed of light translates from elementary time to length, the maximum entanglement speed translates from elementary time to essentially quantum units, essentially h bar. It translates to sort of quantum to distance in branchial space. So there is a translation from elementary time to distance in rule space, and that distance in rule space is somehow related to program length. And so there's a way, I think, of connecting program length, which has always been this rather abstract thing, to something sort of physical. Don't yet fully understand that, but I think it's a coming attraction, so to speak. Okay, next question from Peter here. does the theory predict how the universe ends? No, we don't know that. We strongly suspect if that the universe will go on forever, that it corresponds to a computation that will not halt. There's a whole bunch of reasons to believe that in this kind of model, but we can't say that for certain. I mean, there is the possibility that this computation will eventually reach a final state where it just says, and the answer is 42 or whatever. But it seems very unlikely. That would, it's very hard to make that consistent with causal invariance. It's hard to make that consistent with things we already know are true about the universe, but it is not absolutely ruled out by this kind of model. Okay, if experiment produced a Turing oracle or a hypercomputer, would that disprove the theory? Yes, that would disprove this theory. However, good luck on connecting such a hypercomputer to anything that our senses can deal with, because in everything we've done in science, we have tried to reduce what we observe in science to essentially symbolic representation. And a symbolic representation is a finite symbolic representation, and it is incapable of representing the kinds of raw material that you need to actually interact with a hypercomputer. So even if we had a hypercomputer sitting under our noses, we wouldn't know it because we just don't have a good way to interact with a hypercomputer because of the fact that our way of describing things and even probably thinking about things is rooted in kind of this symbolic notion of doing things. Somebody's asking, can we get a copy of the project's book signed by Jonathan, Max, and me? Sure. We were considering, as we thought about this project, and we tried to understand what things we could provide for people in this project, and how people could be involved. I have to say that swag was up there in the list, and kind of the adopt the universe kind of idea from the registry is also something that's on the list. And so we're hoping to be able to provide some of those things, but mostly we're just really keen. I mean, we see this as being a sort of a big intellectual adventure. It's kind of like, can we climb the tallest possible Mount Everest of science? We don't know if we'll get to the top, and we don't know whether it'll take a century to get to the top, but we think it'll be fun to see what happens on the climb. And we hope other people will help in that climb, but we hope also that people will find it interesting to see what's involved in getting there, and to see what in our efforts to kind of do sort of frontline science, what's actually involved in doing that. Let's see. So a question here: do the updates to the hypergraph happen in parallel? What happens in the case of collisions? Yeah, that's the whole point. There are many possible updatings that can occur, and the fact that there are those possible updatings defines this multi-way system, which is the source of quantum mechanics. And what does it mean that they operate in parallel? Well, there's a set of causal relationships where one thing has to have occurred before another can occur. That defines the causal graph. It defines a partial ordering of those kinds of update events, and it's the whole story of what possible sort of total orderings are consistent with that partial ordering, which translates into what do we consider this sort of the successive steps of time in our universe. That's kind of how the whole thing sort of works out. And it's this invariance of the ordering of what happens when things occur in parallel that corresponds to causal invariance, that implies special relativity, that implies sort of objectivity in quantum mechanics, etc. So yeah, it's a very critical thing that these things can happen in parallel, and that the quotes collisions, those collisions are precisely the sort of those lead to the entanglements, so to speak, that happen in quantum mechanics and so on. How can the nominal average guy contribute to this project? We're going to have a distributed computing mechanism where you can run some little fragment of searching for the universe on your computer. That's nice way to contribute. I would say that we don't know what kinds of thinking are going to be needed to figure out everything that needs to be figured out here. And there's a lot of kind of both. I mean, some aspects of this are going to be at the front lines of sort of quantum field theory, general relativity, those kinds of things. They kind of need sort of a PhD's worth of physics knowledge to really be fully engaged in them. But there's a lot that's happening at sort of the computational level where, you know, we're operating really from the ground up. We don't know anything yet. I would say that a lot of the work that I did in New Kind of Science and so on, exploring different kinds of systems, there's a lot to do there, and there's a lot of intuition to build. You know, I mentioned using string substitution systems as a way to get an understanding of the multi-way graph and so on. There's a lot more that can be done along those lines, and this is a very young field. So there's a lot that can be done by, you know, without having a physics PhD. There's a lot that can be done by just doing computational experiments, trying to make conclusions from these computational experiments, trying to devise kind of general principles on the basis of those experiments. And I don't think anybody has a great advantage in doing that. I mean, I've been doing that kind of thing for 40 years now, so I kind of have developed a certain amount of intuition about it and can do these things at a certain speed. But in particular, the tools that we have in Wolfram Language, part of the reason I built Wolfram Language was to have what I needed to be able to do those explorations. So those tools are very well optimized for those kinds of explorations. And as I mentioned, the Wolfram Language functions and things for doing evolution according to these hypergraph models and so on are all, as of today, available through our function repository, and you can get them through the website and so on. And so you can explore these things. And, you know, it's really an open field. Nobody's explored these things. You know, we've just started. We've just been picking away at the edge of it. So I think exploring kind of both these full hypergraph rewrite systems, those are just a bit complicated, but exploring these analogs and string rewriting, even in things like cellular automata, highly useful. And it's just like this, it's a really wide open field where there's just a huge amount to do. And I think my only, you know, one of the things that's happened from my work on New Kind of Science is, you know, I really pushed this idea that one can make models for things in the world, for just things in nature, things in social science, whatever, on the basis of programs rather than mathematical equations. And it's really a pretty neat thing that's happened in the past probably 15 years. And I'm not saying that it's all my fault, so to speak, but I think the New Kind of Science book kind of was, you know, that was really the idea that I really pushed in that book was this idea: use programs to make models of things rather than using mathematical equations. And after, you know, it's basically been a 300-year run of people primarily using mathematical equations to make models of things. Last 15 years, there's been a pretty thorough transition to using programs to make models of things. And that's a pretty neat thing to see. It's something, it's kind of, to me, it's a little ironic because a bunch of people, when my book came out, said, couldn't possibly work, never going to be useful. Programs never useful for anything. And now that's basically what everybody does. So that's kind of nice. But the one area where that really hadn't made progress is in fundamental physics, where the idea of using programs to make models of things hadn't made progress is in studying fundamental physics. And I think now we kind of cracked that nut of seeing how one can use programs and computational ideas to model fundamental physics. So that's something that I'm sort of excited about here. But I think, as I say, the best contributions to be made, you know, if you really want to get into the intellectual meat of this, is study simple programs, study what they do, either the real full hypergraph case or the simplified cases, and try and build up principles about what happens and try and find phenomena. You know, you might find some weird kind of new singularity that corresponds to some bizarre sort of mixed quantum mechanical relativistic black hole or something. You could find that by just studying these hypergraphs and the evolution of these hypergraphs. The trick in these things is always, you see some weird phenomenon on the screen. The thing that's just maddeningly difficult is understanding what does that really mean. But there's a lot that can be done by just saying, in the simple cases, just look at these cases, make a systematic study, describe what you see systematically, And that's part of the building block that can make science. And that's what a lot of science is. Just good science is about doing things systematically, being able to have a good presentation of what you find, and so on. I mean, I would say that in this project, the thing that sort of happened over the sort of 40 years or so that I've been sort of picking away at things somewhat related to this, it's been sort of a gradual understanding of more and more of what the significance of things is, and a gradual realization that, you know, often it's that thing that I sort of understood, I sort of had seen, but I didn't really understand its significance. And then I progressively understand more and more of its significance. And that's typically the slow part, at least in my experience. All right, we should take a few more questions and then probably wrap this up for today. Let's see, what amount of simulation is required before enough information can be found to compare the rule to existing theories? We don't fully know the answer to that. I've said this several times here. I mean, we just don't know. We don't know. What's special about the universes in the registry of notable universes? I think we haven't finished, actually. We were rerunning the registry just last night, and I think they didn't finish running. So I think we've got about 1,000 universes. Those are really just universes that came out of various searches. They were based on various criteria. They seem to have some interest or another. They're really pretty arbitrary. I mean, that's just the universe that just does nothing or makes this very simple tree. Those don't make it for the registry. These universes that for one reason or another, it's like, oh, that's kind of interesting. Put them in the registry. We're sort of over-generating things for the registry in the hopes that we'll capture things that will be useful examples to study. And talking about, you know, what does the average person do in this project? You know what? We haven't even looked at every page in that registry. We don't know what's on there. We don't know what, there may be a bunch of really weird and interesting phenomena there that we haven't even seen yet. So that would be a good place to start. Let's see. Does the theory explain whether a hot dog is a sandwich? You know, one of the things this theory says is there's a lot about the way we perceive things that is in the matter of how we perceive them. And so I don't think we have anything directly to say about that, other than that there are different description languages for the world, and that there's sort of equivalence between these different description languages, and it doesn't answer your question. This is somebody commenting that they like what Jonathan had to say. I do too. Jonathan has been a great contributor, as Max has also, to this project. And I hope tomorrow Jonathan will be a big part of the more technical explanations that we're giving. This question here, can we explain the principle of least action in the context of hypergraphs? The answer is basically yes. We can reproduce the path integral of quantum mechanics, from which you can derive the mechanical principle of least action. And the way that works, as I was mentioning, is it's kind of the analog of things, sort of the analog of Einstein's equations in branchial space rather than in physical space. And that's what that's what leads to this. On using the Turing completeness of the rules to do massive computations using tiny structures in the network. That's kind of how the universe is building itself for us, I think, all the time. Is it's doing I mean, one of the things that really took me a while to come to terms with is this universe is such a waster of computation. I mean, there's just unbelievable amounts of computation happening to just maintain a little tiny piece of space. And that's something very weird. Now, can we harness that computation for something that we think is useful? I think it's useful to maintain space, but can we harness the computation, you know, in a way that's sort of purposeful to us? We don't know how to do that yet. That's obviously a very interesting thing to think about. The length scales that are involved here are really, really tiny, so that's a challenge, but there may be ways to do it. Okay, so there's a question about low entropy at the Big Bang. Yeah, I think I talked about that a little bit. What I think is happening is that the initial conditions may be very simple, but essentially what's happening is that the evolution, the irreducible computation that's happening in the evolution of the system is so encrypting those initial conditions that for us as sort of computationally limited observers, we can't decrypt that. And when we can't decrypt it, it looks random to us. So it looks like it has high entropy. And it's that phenomenon that leads to the second law of thermodynamics and the apparent increase of entropy and the low entropy of the initial, which means that we can start from this low entropy, this very simple initial condition, and wind up with this higher entropy, with the law of entropy increase and so on. Do we get comments from established physicists already? Oh yes, lots. It's been kind of interesting. We haven't had, partly because of the pandemic, we haven't been sort of communicate as much as we might. We had only one sort of fully interactive session with a group of friends of mine who are sort of established physicists. It was a lot of fun, as I would say. They were getting it, which is really good, and they were like, this is really neat. So that's good. I've been, just in the last 24, 48 hours, we've been sending out sort of preliminary versions of some of this stuff. And I'm sure while I've been on this live stream, I've had a whole bunch of other responses. What's interesting here is the methodology, the underlying methodology is a bit alien. But as soon as we've gotten up to the level of sort of connecting to things like quantum field theory and general relativity, it's actually quite familiar. And as I mentioned, one of the really nice things is this correspondence to a lot of kind of theories that have emerged, particularly in the last decade or so in physics, particularly as coming out of this ADS-CFT correspondence and so on. And I think that really helps in making this connection to sort of I used to be an established physicist, so the established physicist is probably the wrong description. I think I'm part of that group, although I've been kind of out of the business for a long time now. What's happened? It's kind of a funny sort of time warp for me because a lot of the people who've been sort of leading physicists were friends, colleagues of mine back when I was doing physics. I happen to be a bit younger than most of them because I started doing physics when I was pretty young. So it's been really strange for me because I've been following physics all these years, but I haven't been really deeply involved in it. It's kind of interesting for me to go back and look, okay, what happened to this particular thing? One of the things that has happened actually in physics is that there were many different strands of development that existed. And one of the things that has happened in sort of the established physics kind of thing is a lot of those strands have merged in different ways. So things that would be in completely different papers will now find themselves as words in the same sentence. And actually that unification, I think we can take that a lot further with this theory. But the fact that we're kind of relating to a lot of those things, I think is very helpful in making a connection to physics. One of the things that, I'm really hopeful that we'll be able to leverage what people have already studied, and a lot of the sort of technical work in string theory, twistor theory, all these kinds of things will be, oh, okay, that means we can say this and this and this, in addition to what we've been able to say. And one of the things we hope to do on our live streams is have discussions with some of the leaders in those various fields, many of whom I think I would consider to be friends of mine from back in the day when I used to do physics, be able to talk about how their theories and the mathematical development of their theories particularly relates to what we're doing here. How does this compare with defining a context-free grammar for physics? Well, okay, so these hypergraph rewriting rules are like graph rewriting rules. Typically, context-free grammars operate on strings, just sequences of things. These are like graph grammars. The theory of graph grammars is not particularly well developed, but you can think about these things as being kind of like hypergraph grammars, except that our objective is a little different from a typical grammar. In typical grammar, what you're trying to do is say, parse this English sentence, for example, or parse this piece of programming language code or something. and you're saying, break it down, make a tree out of it. And you're doing that by saying there are these rules, and I'm going to reduce the thing down to the tree that could be used to generate it. What we're doing instead is sort of running that process in reverse, and we're saying, take this starting point and sort of do all the possible treeing out of what could happen. And in some sense, what we're doing is like running a graph grammar kind of in reverse, running a hypergraph grammar kind of in reverse. And that's sort of what is really going on here. And we are the intermediate, our whole existence and the whole universe is the intermediate stages, the non-terminal nodes, effectively, in the running of that hypergraph grammar in reverse. Is it possible to write unit tests that would validate the presence of certain physics analogous features when a particular rule is run? So, gosh, how to think about that? Okay, let me try and take that in the following way. So one of the things about existing science, particularly experimental science, is the idea of doing isolated experiments. So in experimental science, the typical thing you try to do is to say, I'm going to do an experiment on this piece of this system and nothing else matters. I'm going to be able to try and isolate the effects in this particular